Antarctica hides a secret humanity was never meant to decode. Scientific instruments capture signals that defy every known explanation, pulsing under miles of ice that should be empty. What if satellite readings reveal engineered geometry sealed away by forces no agency admits tracking? Every expedition returns with unexplained temporal gaps. At the edge of the McMurdo Dry Valleys in Antarctica, a slow-moving tongue of ice spills out from Taylor Glacier, and from its terminus emerges something that immediately breaks the expected palette of the continent. Against the surrounding white and blue, a deep crimson stain seeps into the frozen landscape. It appears almost like a wound in the ice itself, steady, persistent, and strangely alive in appearance. This feature is known as blood falls. First documented in 1911 by Australian geologist Thomas Griffith Taylor during the Terra Nova expedition, it has remained one of Antarctica's most visually arresting and scientifically intriguing phenomena. At the time, early explorers could only speculate about the source of the red flow. The image of iron-rich water spilling from a glacier in one of the driest places on Earth seemed almost contradictory. For decades, the explanation remained uncertain. Later studies revealed that the water is not surface melt in the traditional sense, but a highly saline brine trapped beneath the glacier. This liquid reservoir exists in a subglacial environment cut off from sunlight and atmospheric exchange for potentially millions of years. When the pressurized brine escapes through cracks in the ice, it encounters oxygen at the surface and undergoes a chemical transformation. The iron within the water oxidizes, producing the rust-like red coloration that gives blood falls its name. Yet even with this explanation, the setting invites deeper questions. How does liquid water remain stable in such extreme cold? The answer lies in salinity. The trapped brine contains such high concentrations of salt that its freezing point is significantly lowered, allowing it to persist in a liquid state beneath the glacier. This phenomenon suggests a hidden hydrological system beneath the ice, one that behaves differently from surface conditions we are accustomed to observing. In recent decades, research has also uncovered biological implications. Microbiological studies have identified microbial communities within the brine, organisms that survive without sunlight, relying instead on chemical processes, particularly iron and sulfur compounds, for energy. These microbes exist in isolation, forming an ecosystem that operates on an entirely different metabolic framework from surface life. Their presence raises questions about the limits of habitability on Earth and, by extension, elsewhere in the solar system. Still, not every aspect of this system is fully resolved. The geometry of the subglacial reservoir, the full extent of its connections beneath Taylor Glacier, and the long-term stability of its isolated water remain active areas of research. Some models suggest a complex network of brine channels and ancient trapped seawater, possibly remnants from a time when sea levels and ice coverage were vastly different. Others propose a self-contained system slowly evolving under geological pressure, independent from external influence for immense spans of time. There are also broader interpretive ideas that circulate in scientific discussions, though often cautiously framed. Could such isolated systems represent analogs for extraterrestrial environments, such as the subsurface oceans of icy moons? What might these extreme microbial ecosystems reveal about life under conditions once thought entirely uninhabitable? While these questions remain grounded in scientific inquiry, they also highlight how little is still understood about life's adaptability in isolated cryogenic environments. Standing before blood falls today, one is struck not only by its color, but by its persistence. A steady flow of crimson emerging from silence, unchanged in its essential behavior since it was first recorded over a century ago. It invites observation, measurement, and interpretation, but resists complete closure. And so the question lingers in the frozen air of the dry valleys. How many other hidden systems lie sealed beneath the ice, quietly operating beyond sight, waiting for the moment they reveal themselves in ways we have yet to understand. From the crimson seep of blood falls, where liquid chemistry survives beneath ancient ice, the story of Antarctica shifts inward again, away from what can be seen on the surface, and toward what can only be measured in faint, passing distortions of data. Far across the continent, in regions where the ice sheet rises like a pale continent of its own, scientists have installed listening stations designed not for sound in the traditional sense, but for radio frequency signals. One of the most significant efforts is embedded within the Antarctic ice itself. The IceCube Neutrino Observatory, a vast detector buried deep beneath the South Pole. Its purpose is not to capture conventional transmissions, but to observe elusive subatomic particles passing through Earth, neutrinos, by detecting the faint flashes of light they produce when interacting with ice. And yet, in the process of listening for the universe, something unexpected has occasionally surfaced. Over years of observation, researchers working with Antarctic detection systems have recorded brief radio pulses and anomalous signals that do not always align neatly with expected models. Some originate from known sources: cosmic rays striking the atmosphere, solar activity interacting with Earth's magnetic field, or human-generated interference carried across long distances. Antarctica's ionosphere, shaped by extreme solar conditions and magnetic proximity to the pole, can bend and distort radio waves in unusual ways, creating echoes and refractions that complicate interpretation. But not every signal fits comfortably within these frameworks. During high-altitude balloon experiments such as those conducted by the ANITA experiment, designed to detect radio pulses generated by cosmic neutrinos interacting with ice, researchers have reported events that appear to originate from angles difficult to reconcile with standard particle physics models. Instead of descending from space and passing through the ice, some signals seemed, at least in preliminary interpretations, to emerge from below the horizon, as if passing through the Earth itself. These observations remain rare, debated, and carefully re-examined. Alternative explanations have been proposed: subtle reflections from ice layers, instrumental effects, or statistical anomalies that emerge in highly sensitive equipment operating at the edge of detectability. In science, especially at this frontier, ambiguity is not unusual. It is expected. The Antarctic environment itself is a known amplifier of uncertainty, where temperature gradients, ice stratification, and atmospheric layering can all distort incoming data in unexpected ways. Still, the question lingers in the background of these measurements. Why do some signals appear inverted? Why do they arrive in patterns that do not immediately correspond to known astrophysical sources? To broaden the search, other systems, such as the RICE experiment, have attempted to detect ultra-high-energy neutrinos using radio antennas embedded within the ice. These instruments listen for nanosecond-scale pulses, so brief they exist almost at the threshold of physical measurement. In this domain, even the smallest irregularity becomes significant, and every unexplained spike must be carefully catalogued, tested, and either explained or set aside as unresolved. Outside the realm of particle physics, Antarctic research stations also monitor very low-frequency, VLF radio waves that travel between the Earth's surface and the ionosphere. These waves can be influenced by geomagnetic storms, lightning activity across the globe, and shifts in solar radiation. Occasionally, unusual fluctuations are recorded, brief distortions that do not clearly match known environmental drivers. While most are eventually traced to natural causes, a small number remain difficult to classify with certainty. What makes Antarctica unique is not only its isolation, but its silence. With minimal human infrastructure across vast distances, the continent becomes a natural laboratory where background noise is reduced, allowing faint signals, whether cosmic, atmospheric, or instrumental, to stand out more clearly than they would elsewhere. But that same clarity also magnifies uncertainty. When everything else is stripped away, even minor irregularities feel more pronounced, more difficult to ignore. Some researchers interpret these anomalies as opportunities, signposts pointing toward new physics or undiscovered interactions between particles and ice. Others view them as reminders of the complexity of measurement itself, where instruments operate at the edge of what is possible, and where nature and noise can sometimes look indistinguishable. And so the recordings continue, day after day, season after season, beneath a sky that is often empty of human presence but never truly silent in its electromagnetic background. From the faint distortions of Antarctic radio silence, where signals appear and vanish like echoes from an unseen boundary, the narrative shifts once more, away from the instruments above the ice and downward, into a world that has not seen light for millions of years. Far beneath the East Antarctic ice sheet lies a void so vast it was once invisible to science itself. A smooth, frozen plateau stretches above it, undisturbed by wind or time on the surface. Only after decades of radar mapping did researchers realize that beneath nearly 4 kilometers of ice, there is not bedrock, but water. This is Lake Vostok, one of the largest subglacial lakes on Earth. Roughly the size of a major inland sea, it has been sealed beneath the Antarctic ice for an estimated 15 to 25 million years. Isolated from sunlight, atmosphere, and surface ecosystems, it exists in a state of permanent darkness, held under immense pressure and sustained by geothermal heat rising from below. The existence of such a lake was first inferred in the mid-20th century through Soviet-era radar surveys, and later confirmed through satellite measurements and ice-penetrating radar technology. What began as an anomaly in reflection data gradually resolved into something far more structured. A deep, liquid body hidden beneath one of the coldest environments on Earth. Above it sits Vostok Station, one of the most isolated research outposts on the planet. For decades, it has served as both a scientific gateway and a symbolic threshold between the known surface world and the concealed environment below. Mainstream scientific understanding suggests that Lake Vostok remains liquid due to geothermal heat and the insulating properties of the ice above it. The immense pressure from the glacier prevents the water from freezing solid, while heat from the Earth's crust maintains a delicate balance. In this view, the lake is not an anomaly, but a natural consequence of geology and glaciology operating over immense timescales. Yet the very conditions that make Lake Vostok explainable also make it profoundly difficult to access. Drilling into it requires penetrating kilometers of ancient ice, each layer preserving a record of atmospheric history stretching back hundreds of thousands of years. Scientists have been careful to avoid contamination, recognizing that even a small intrusion could permanently alter whatever isolated environment exists below. And so the lake remains largely unvisited. Samples taken from the ice above it have revealed microbial traces, organisms that appear adapted to extreme cold, pressure, and darkness. But whether these organisms originate directly from the lake itself or from contamination during drilling remains a subject of careful scrutiny. In parallel with established findings, more speculative interpretations have emerged in discussions far beyond mainstream research. Some have wondered whether such a long, isolated body of water could preserve biochemical processes unlike anything observed on the surface. Others have asked whether Lake Vostok could function as a natural laboratory for prebiotic chemistry, where life, if present, might have followed a completely separate evolutionary trajectory. There are also broader, more cautious questions that scientists themselves occasionally raise. What does it mean for an ecosystem to exist entirely without sunlight? How stable is such a system over millions of years? And if life can persist here, what does that imply for similar environments beneath the icy crusts of other worlds, such as Europa or Enceladus? In this sense, Lake Vostok is often described not as an isolated curiosity, but as a potential analog, an earthbound reflection of environments that may exist far beyond our planet. Yet even this comparison does not resolve the deeper uncertainty that surrounds it. Because despite decades of study, no one has directly observed the lake in its untouched state. Its waters remain sealed beneath ice that has never been fully breached without concern. Every measurement, every core sample, every radar echo is an indirect interpretation of something still physically out of reach. And so the image persists. A vast, hidden body of water, suspended in darkness beneath kilometers of ancient ice, holding within it a history that predates human civilization entirely. As the Antarctic investigations continue, from surface anomalies to radio irregularities, and now to this submerged world of silence, one question remains quietly unresolved. When an environment is isolated for millions of years, untouched and unseen, does it remain simply a geological feature? Or does it become something we have not yet found the language to fully understand? From the sealed waters of Lake Vostok, hidden beneath kilometers of ancient ice, the story of Antarctica continues its descent into deeper obscurity, moving not only downward into subglacial worlds, but outward into structures that should not exist beneath a continent long thought to be geologically quiet at its core. Far beneath the East Antarctic ice sheet, under layers of ice that have accumulated over tens of millions of years, lies a mountain range that was never seen directly by human eyes when it was first discovered. No surface peaks break the horizon. No ridgelines interrupt the endless white expanse above. And yet, beneath the ice, something immense rises. This buried formation is known as the Gamburtsev Mountains, a full-scale alpine system entombed entirely beneath the Antarctic ice sheet. First detected during Soviet Antarctic expeditions in the 1950s and later mapped in greater detail using airborne radar surveys and satellite gravimetry, the range stretches for hundreds of kilometers, with peaks, valleys, and deep mountain basins carved into ancient bedrock. What makes the Gamburtsev Mountains extraordinary is not only their size, but their isolation. Unlike most major mountain ranges on Earth, they are not visible at the surface. They exist entirely beneath nearly 4 kilometers of ice, hidden as if the continent itself were concealing its own internal architecture. Their elevation rivals that of major mountain systems exposed elsewhere on the planet, yet they remain completely buried, preserved in a frozen state of geological secrecy. Mainstream geology suggests that the Gamburtsev Mountains likely formed hundreds of millions of years ago during ancient continental collisions, possibly linked to the assembly and breakup of supercontinents long before Antarctica assumed its current position at the South Pole. Over time, erosion and tectonic stability left the range intact, while successive ice ages gradually buried it under layers of accumulating ice. In this interpretation, the mountains are not unusual in origin, only in circumstance. They are remnants of deep time, preserved beneath a cryogenic cover that shields them from erosion, weathering, and human observation. And yet, even with this explanation, the presence of such a large and well-structured mountain system beneath the heart of the Antarctic ice sheet raises quiet questions. How does a landscape of such complexity remain so sharply preserved? What does it mean for an entire orogeny to exist in a state of permanent concealment, exerting influence on ice flow, subglacial hydrology, and the shape of the continent above it? Radar and seismic studies indicate that the Gamburtsev Mountains play a significant role in shaping the behavior of the ice sheet itself. The ice flows around them, over them, and through deep valleys carved into the bedrock, suggesting a hidden topography that actively interacts with the frozen world above. In this sense, the mountains are not inert. They are part of a dynamic system, influencing the movement of ice across an entire continent. Some researchers have noted that the range appears unusually pristine for a formation of its presumed age. with sharp features that seem less degraded than comparable ancient mountain systems elsewhere on Earth. This observation has led to careful discussions about the thermal and erosional history of the region. Was the area long protected from major tectonic activity? Did the ice sheet itself preserve the landscape in a way that slowed or altered expected geological decay? Beyond established science, more speculative interpretations occasionally emerge in broader discussions about Antarctic geology. If the continent has remained isolated and ice-covered for such vast spans of time, could there be features beneath the ice that reflect not only ancient tectonics, but also long-term climatic insulation on a planetary scale? Could hidden mountain systems like the Gamburtsev Range preserve clues about earlier Earth environments that no longer exist at the surface? These questions remain open, not because they contradict established understanding, but because direct access is limited. Every map of the range is constructed indirectly, through radar pulses, gravity anomalies, and ice penetration models. No expedition has ever walked its valleys. No human eye has ever seen its peaks. And so, the Gamburtsev Mountains remain one of Antarctica's most profound paradoxes. A vast alpine world hidden beneath an ocean of ice, known in outline but never in presence, mapped but never touched. As the exploration of Antarctica's hidden systems continues, from crimson subglacial flows to silent radio anomalies, from sealed lakes to buried mountain ranges, one question continues to surface in different forms. How much of a continent can remain unseen before our understanding of it becomes only a reflection of what lies beneath our instruments, rather than beneath the ice itself? From the hidden architecture of the Gamburtsev Mountains, where ancient peaks lie entombed beneath kilometers of ice, the Antarctic story shifts once more, not only into what is buried, but into what may still be alive beneath the continent's frozen crust. Far below the East Antarctic ice sheet, where pressure is immense and light has never reached, scientists have identified something unexpected: heat, where there should be stillness. Radar surveys, seismic readings, and gravity measurements have revealed regions where the ice behaves differently, melting from below, reshaping its own base in ways that suggest a source of geothermal energy far more active than once assumed. These are the suspected subglacial volcanoes, volcanic systems hidden beneath the ice, buried so deeply that their forms are invisible to the surface world, yet influential enough to subtly reshape it. One of the most studied regions lies within West Antarctica, particularly the area known as the West Antarctic Rift System, where the Earth's crust is thinner and more geologically dynamic. Here, heat from the mantle can rise more easily toward the surface, interacting with the base of the ice sheet. In some locations, scientists have identified geothermal hotspots, areas where melting occurs at rates inconsistent with the surrounding environment. In a continent defined by cold, the presence of heat beneath the ice introduces a quiet contradiction. Mainstream geological understanding explains these features as remnants of tectonic processes stretching back millions of years. Antarctica, once part of the supercontinent Gondwana, experienced extensive volcanic and rifting activity during its geological past. Even today, residual heat from the Earth's interior continues to escape through thinner sections of crust, particularly in regions of tectonic extension. In this view, subglacial volcanic activity is not unexpected. It is a continuation of Earth's slow internal evolution. And yet, beneath the ice, the evidence is rarely direct. No lava is observed erupting into open air. No volcanic cones are visible on the surface. Instead, scientists interpret indirect signals: patterns of ice flow acceleration, localized melting at the base of the ice sheet, and chemical signatures in subglacial water systems that suggest geothermal influence. In some cases, ice cores have revealed traces of volcanic ash embedded within ancient layers, indicating past eruptions that may have occurred under or near the ice sheet itself. These layers serve as silent markers of a more dynamic geological past, preserved within the frozen archive of Antarctica. But questions remain. If heat sources exist beneath such thick ice, how stable are they over time? Could they influence the long-term behavior of the ice sheet in ways that are still not fully understood? Some models suggest that subglacial volcanic activity could contribute to localized melting, potentially affecting ice sheet movement and stability. Others propose that these geothermal systems might be more widespread than currently mapped, hidden beneath regions where data resolution remains limited. Beyond established interpretations, more speculative ideas occasionally surface in broader discussions. Could clusters of geothermal activity beneath the ice interact in ways that create temporary subglacial water networks? Could heat pockets influence the formation of subglacial lakes or alter the basal structure of ice sheets in ways that are not yet fully modeled? These ideas remain unconfirmed, explored only within the boundaries of theoretical research. What is clear, however, is that Antarctica is not entirely thermally silent. Beneath its frozen surface, the planet continues to breathe, slowly, unevenly, and in places we are only beginning to map. In this sense, subglacial volcanoes are not simply geological curiosities. They are reminders that even in the coldest environment on Earth, internal planetary forces remain active, shaping landscapes that no human has ever directly witnessed. And so the ice above becomes something more than a static shield. It is a thin, reactive layer above a restless system, one that moves, melts, and reforms in response to forces hidden far below sight. As the exploration continues from buried mountains to hidden lakes, and now to heat rising from within the Earth itself, another question quietly emerges. If Antarctica conceals both ancient stone and living geothermal energy beneath its surface, what other interactions between fire and ice might still be unfolding beyond the reach of our current observation? From the hidden heat rising beneath subglacial volcanoes, where geothermal forces quietly reshape the underside of Antarctica's ice, the narrative returns once more to the surface, but not to silence. Instead, to a place where the ice is not only a barrier, but a detector. At the geographic center of the continent, where temperatures plunge and the air itself feels suspended in stillness, a vast lattice of sensors is buried deep within the ice sheet. Cables descend through drilling shafts more than a kilometer long, disappearing into a medium so clear and ancient that it preserves faint flashes of light like frozen time itself. This is the world of the IceCube Neutrino Observatory, one of the most ambitious particle detectors ever constructed. Its purpose is not to observe Antarctica itself, but to use Antarctica as a lens, to capture neutrinos, nearly massless particles that pass through matter almost entirely unimpeded. These particles stream constantly through Earth, born in distant cosmic events, exploding stars, active galactic nuclei, and other high-energy processes across the universe. When a rare neutrino interacts with the Antarctic ice, it produces a faint, blue flash of Cherenkov radiation, recorded by sensors embedded deep below the surface. For the most part, the system behaves as expected. Most detected events align with established models of cosmic particle physics. They descend from above, pass through the atmosphere, and occasionally interact within the ice. The data builds a growing map of high-energy activity in the universe, silent, invisible, and continuous. But within this steady stream of observations, something unusual has occasionally appeared. Certain events, recorded over years of observation, have raised careful scientific attention due to their apparent trajectories. Instead of arriving from space and moving downward through the ice, a small number of signals seem to originate from angles suggesting upward movement, paths that, in simplified interpretation, would imply particles passing through the Earth itself before being detected. These are the so-called IceCube anomalies, subtle and rare enough that they sit at the edge of statistical significance, yet persistent enough to warrant continued investigation. Standard explanations remain firmly grounded in known physics. Some events may result from background noise, rare atmospheric interactions, or complex scattering effects within the ice. The Antarctic environment itself is not uniform. Layers of ice with different densities, impurities, and crystal structures can subtly distort the propagation of light, complicating reconstruction of particle trajectories. In high-sensitivity instruments, even minor uncertainties can produce patterns that appear unusual when viewed in isolation. Still, the questions persist in the data. Why do some reconstructed paths defy simple geometric expectations? Why do certain signals appear from angles that challenge conventional interpretations of particle propagation through the planet? And why do these anomalies, though rare, continue to appear even as detection methods improve? To explore these questions, scientists refine models, run simulations, and cross-check results with other observatories around the world. The goal is not to find mystery, but to eliminate uncertainty. Yet in doing so, they occasionally encounter results that resist easy categorization. Events that are neither fully explained nor entirely dismissed. Beyond the established framework of particle physics, broader theoretical discussions sometimes emerge. Could there be unknown interactions between high-energy particles and dense matter at extreme energies? Could subtle effects in ice propagation or detector geometry account for the patterns observed? Or are these simply statistical outliers within an immense dataset of otherwise consistent observations? These questions remain open, carefully contained within the language of probability and measurement. And yet, the setting itself adds weight to the mystery. Deep beneath the South Pole, isolated from human activity, the IceCube array listens continuously to a universe that cannot be seen, only inferred. It transforms the Antarctic ice into a kind of cosmic instrument, one that records not only what arrives from the stars, but also how those arrivals interact with the hidden structure of our own planet. In this sense, Antarctica becomes more than a passive landscape. It becomes a medium of revelation, where the universe leaves faint signatures in frozen silence. As the anomalies accumulate in the background of ongoing research, one question remains suspended in the data. When a signal appears to pass through the impossible, are we witnessing a limitation of our instruments, or a hint that the universe still holds pathways we have not yet fully understood? From the deep interior of the IceCube detector, where neutrinos pass silently through Antarctic ice and leave only the faintest traces of light, the narrative returns to the surface world, but not to stillness. Instead, to movement, to openings in a place that should be sealed. Far from the interior plateau, at the edge where the Antarctic continent meets the Southern Ocean, the ice sheet breaks into floating shelves that extend outward like frozen fingers. Here, in the frozen boundary between land and sea, something unusual has repeatedly appeared. Vast openings in the sea ice where open water emerges unexpectedly, surrounded by an otherwise continuous field of ice. These are known as Weddell Sea Polynyas, regions of open water that form within or adjacent to sea ice, often in locations where ice would normally be expected to remain solid and unbroken. One of the most famous examples occurred in the mid-1970s, when a massive recurring polynya appeared in the Weddell Sea, persisting over multiple winters and spanning an area larger than some countries. Then, as suddenly as it formed, it disappeared. Polynyas are not unknown in polar science. In mainstream understanding, they are typically explained through well-established processes. Strong winds can push sea ice away from a fixed point, creating openings. Ocean currents can bring relatively warmer water upward, preventing ice formation. Subsurface convection can also play a role, especially in regions where salinity and temperature gradients interact in complex ways. In this framework, Weddell Sea Polynyas are natural expressions of a dynamic polar ocean system, temporary disruptions in an otherwise stable cryosphere. And yet, the scale and persistence of some of these openings have invited deeper examination. Unlike small coastal polynyas that form regularly in predictable patterns, the large Weddell Sea event observed in the 1970s was both expansive and sustained. Satellite observations confirmed a recurring cycle of opening and partial closing, suggesting a system that was not simply transient, but rhythmically active over time. Oceanographers have pointed to deep convection processes as a possible explanation. In this model, dense, cold surface water sinks, drawing warmer, deep water upward in a cycle that can inhibit ice formation. This vertical mixing can, under certain conditions, create stable zones of open water, even in extreme cold. But the Southern Ocean is not a simple environment. Beneath its surface lies a layered structure of currents, salinity gradients, and heat exchanges that are still being mapped in detail. In some regions, the interaction between ocean and ice shelf is influenced by meltwater channels flowing from beneath continental ice formations, linking surface openings to processes occurring far below the ice sheet itself. This connection between surface polynyas and sub-ice systems raises broader questions. Could openings in the sea ice reflect not only atmospheric and oceanic dynamics, but also deeper interactions between ice shelves and the ocean below them? Could the release of fresh water from melting ice sheets subtly influence where and when these openings appear? Some researchers have suggested that polynyas may act as windows into the deeper ocean system, revealing circulation patterns that are otherwise hidden beneath continuous ice cover. In this sense, they are not anomalies, but rare exposures of a much larger, concealed process. Beyond established interpretations, more speculative discussions occasionally emerge in broader conversations about polar environments. Could recurring polynyas indicate long-term cycles in ocean heat transport that are not yet fully understood? Could they be linked to shifts in deep water formation, affecting global ocean circulation on a scale that extends far beyond Antarctica itself? These ideas remain theoretical, explored through modeling rather than observation. What remains consistent, however, is their unpredictability. Even with modern satellite monitoring, polynyas can appear, expand, and vanish without clear long-term repetition. Their timing resists simple forecasting, and their behavior continues to challenge complete predictive modeling. Standing at the intersection of ice and ocean, these openings represent more than just gaps in the frozen surface. They are interruptions in continuity, places where the expected solidity of Antarctica gives way to motion, exchange, and uncertainty. And so, as the exploration moves from buried mountains to hidden lakes, from geothermal heat to particle anomalies, and now to these shifting openings in the sea ice, another question emerges quietly in the background. When the most stable regions of Earth's coldest continent begin to open and close without full explanation, what other processes might be unfolding beneath the surface of what we assume is still? From the shifting openings of the Weddell Sea Polynyas, where the ocean briefly reveals itself beneath a continent of ice, the narrative turns inward again. Not to what is visible, but to what can be heard through the frozen silence of Antarctica itself. Deep within the Antarctic interior, far from the coastal fractures and oceanic movement, travelers and researchers have long reported an unusual phenomenon. The ice itself appears to produce sound. Not wind over snow, not the cracking of glaciers under stress, but low-frequency resonances that seem to rise from the frozen ground itself. In an environment where sound is often absorbed and muted, these events stand out precisely because they should not be so easily perceived. These are often referred to as Antarctic booming ice sounds. They are typically described as deep, echoing pulses, brief but powerful vibrations that travel through the ice sheet and radiate outward across the surface. Some sound like distant thunder trapped beneath the ground. Others resemble mechanical resonance, as if something vast were shifting slowly under immense pressure. Yet they occur in regions where no obvious external trigger is present. Mainstream explanations begin with the physics of ice itself. As temperatures fluctuate, even slightly, internal stresses build within the ice sheet. When these stresses are released, fractures can propagate rapidly through the frozen structure, producing acoustic waves that travel long distances. Snow dunes shifting over buried ice ridges may also contribute, as wind-driven movement creates vibrations that amplify through hollow or compacted layers. In this interpretation, the booming sounds are not mysterious at all. They are the natural language of a dynamic living ice sheet responding to temperature, pressure, and gravity. And yet, the nature of these sounds often challenges simple categorization. Some recordings and eyewitness accounts describe patterns that seem too rhythmic, too structured to be entirely random. The intervals between booms can vary in ways that suggest repeating cycles rather than isolated stress fractures. In certain cases, multiple sound sources appear to overlap, creating layered acoustic effects that travel across wide areas of the ice. Scientists have attempted to replicate and model these sounds under controlled conditions, using sensors buried within the ice to capture seismic and acoustic data. In many cases, they confirm that ice movement and cracking are responsible. But even within these datasets, there are moments where the energy signatures do not fully align with expected fracture mechanics. This raises subtle questions about the complexity of ice behavior at extreme scales. Antarctica's ice sheet is not uniform. It is layered, compressed, and structured over hundreds of thousands of years. Within it lie air pockets, buried snow layers, refrozen melt zones, and regions of varying density. When stress travels through such a medium, it may not behave in a simple linear way. Instead, it may resonate, amplify, or interact with internal structures in ways that produce unexpected acoustic effects. There are also environmental conditions unique to Antarctica that can influence sound propagation. Temperature inversions near the surface can bend acoustic waves, allowing sounds to travel farther than anticipated. The extreme dryness and low ambient noise levels mean that even subtle vibrations can become noticeable over large distances. Still, the experience of these booming events often leaves observers with a sense of something larger occurring beneath the surface of explanation. Not necessarily unknown in origin, but not fully intuitive in expression. Could the ice sheet itself, compressed over millennia, be releasing energy in ways that resemble a slow geological breathing? Could the interaction between surface temperature shifts and deep structural layers produce resonant effects that we are only beginning to measure accurately? Or are these simply rare alignments of known physical processes that appear unusual only because of the environment in which they occur? In more speculative discussions, some have wondered whether these sounds might reflect interactions between multiple subsurface processes: ice movement above, geothermal heat below, and shifting pressures within trapped liquid systems. While these ideas remain unproven, they reflect the broader challenge of interpreting a continent where so much of the structure is hidden from direct observation. What remains clear is that the ice is not silent. It shifts, it responds, and at times it speaks in low, distant echoes that carry across vast distances of frozen terrain. Whether these sounds are simple fractures or complex resonances of a deeply layered system, they remind us that even in the coldest and quietest place on Earth, stillness is never absolute. From the deep, resonant echoes of Antarctic ice, sounds that travel through frozen layers like a buried memory, the narrative shifts once more, this time away from movement within the ice and toward a place where ice is almost entirely absent. In the heart of southern Victoria Land, surrounded by towering mountain ranges and cut off from the flow of the surrounding ice sheet, lies a landscape that appears almost alien in the context of Antarctica. There are no drifting snowfields here, no slow-moving glaciers covering the ground in white continuity. Instead, the terrain is exposed. Dark rock, dry gravel, and valleys so arid that they resemble a desert more than a polar environment. This region is known as the McMurdo Dry Valleys, one of the driest places on Earth. In some areas, it has not rained for nearly 2 million years. Katabatic winds descend from nearby mountains with such force that they evaporate moisture before it can settle, stripping the landscape of snow and leaving behind a barren, almost Martian surface. At first glance, the dry valleys appear to be an exception within Antarctica, a region untouched by the deep ice that defines the continent. But in reality, they are part of the same system, shaped by the same climatic forces that govern the ice sheets only a short distance away. Mainstream science describes the dry valleys as a result of unique atmospheric and geographic conditions. The trans-Antarctic mountains block the flow of ice from the polar plateau, while persistent cold and wind prevent the accumulation of snow. The result is a stable, hyper-arid environment where exposed soil and rock persist over geological timescales with minimal alteration. Within this landscape, researchers have discovered ecosystems that challenge expectations of life in extreme environments. Beneath the surface, in hidden pockets of ice and brine, microbial communities survive in conditions of near-total isolation. Some of these organisms metabolize nutrients in ways that do not rely on sunlight, instead drawing energy from chemical interactions within the soil and ice. And yet, the dry valleys are not entirely still. Occasional meltwater flows appear during brief summer warming periods, carving channels through the barren ground before freezing again. Beneath the surface, hidden lakes, sealed under ice-covered soil, contain liquid water maintained by salinity and geothermal heat. These systems exist in delicate balance, sustained by conditions that are still being actively studied. In recent years, some researchers have observed unusual geochemical signatures in certain subsurface environments within the dry valleys. Variations in mineral deposits and isotopic compositions suggest that water-rock interactions may be more complex than previously understood. These findings have led to careful reevaluations of how fluid systems behave in such extreme cold deserts. There are also broader geological questions that remain open. How long has this region remained in such a hyper-arid state? Has it always been this stable, or has it transitioned through different climatic phases over millions of years? Some models suggest that parts of the dry valleys may preserve conditions that resemble ancient Earth environments from before major glaciation events. Beyond established interpretations, the dry valleys have occasionally attracted speculative comparisons, not because of confirmed anomalies, but because of their stark, almost otherworldly appearance. The combination of exposed rock, extreme dryness, and isolated subsurface water systems has led some to view them as natural analogs for planetary environments beyond Earth. However, within scientific discourse, such comparisons remain strictly conceptual, used primarily for studying extremophile life and planetary geology. Still, even within careful observation, the region carries an atmosphere of unresolved complexity. Vast stretches remain minimally explored in detail. Subsurface structures are inferred rather than directly observed, and the interactions between wind, ice, rock, and hidden water systems are still being mapped at fine scales. Standing in the McMurdo Dry Valleys, one encounters a paradox. A place within Antarctica that feels detached from ice, yet is entirely shaped by it. A landscape that appears static, yet contains hidden cycles of movement and transformation beneath its surface. And so, as the exploration moves from booming ice to hidden seas, from geothermal heat to buried mountains, And now to this exposed desert within the frozen continent. Another question quietly emerges. In a place where even the absence of ice is defined by the presence of ice elsewhere, what other subtle systems might still be operating beneath the surface of what appears, at first glance, to be completely still? From the wind-carved stillness of the McMurdo Dry Valleys, where ancient ground lies exposed under one of the harshest climates on Earth, the narrative turns once again toward something smaller in scale, but no less significant in implication. Not mountains, not lakes, not hidden heat beneath the crust, but fragments, pieces of something that arrived from beyond Earth itself. Across the Antarctic interior, particularly on blue ice fields where ancient layers of compressed snow slowly flow like frozen rivers, researchers have long searched for meteorites. These regions act as natural collection zones. As ice moves, it carries embedded meteorites toward areas where they become concentrated on the surface, preserved in the cold, and visible against the pale landscape. Over decades, Antarctica has become one of the most productive meteorite recovery regions on the planet. These are the so-called Antarctic meteorite fields, quiet expanses where dark stones contrast sharply against the ice, waiting to be identified, cataloged, and studied. And yet, within this well-established scientific process, there are moments that remain less straightforward than the system suggests. The phenomenon of missing Antarctic meteorites does not refer to a single event, but rather to patterns observed over time. Expected concentrations that appear lower than predicted, or search areas where conditions suggest accumulation should occur, but yields remain unexpectedly sparse. In a place where meteorites are naturally preserved and visually easy to detect, such gaps invite careful attention. Mainstream explanations begin with environmental and logistical realities. Ice flow is not uniform. Some regions may transport meteorites deeper into the ice or bury them under snowfall before they can be exposed at the surface. Wind patterns can redistribute surface snow, temporarily hiding specimens. Additionally, search coverage is not constant across all regions of Antarctica. Vast areas remain underexplored due to extreme weather, remoteness, and limited expedition windows. From this perspective, missing meteorites are not truly missing. They are simply not yet found, or redistributed by complex glacial dynamics. But Antarctica's ice is not a simple conveyor belt. It is a slow-moving, deforming system influenced by bedrock topography, temperature gradients, and internal stress structures that can redirect flow in unexpected ways. In certain regions, ice can stagnate, accelerate, or fold, creating zones where material may be concentrated or dispersed in ways that are still being refined through modern modeling. Some researchers have also noted that blue ice areas, where most meteorite recovery occurs, are sensitive to subtle environmental changes. Shifts in wind patterns or snowfall accumulation can alter surface exposure, potentially affecting detection rates over time. In this sense, variability in meteorite recovery may reflect changing surface conditions rather than true absence. Still, the broader distribution of meteorites across Antarctica raises intriguing scientific questions. Why are some regions extraordinarily rich in recoveries while others yield far fewer, despite similar physical conditions? Are there underlying differences in ice flow history that have not yet been fully mapped? Or are we observing the combined effect of multiple overlapping processes that only appear inconsistent at a surface level? Beyond standard explanations, some speculative discussions have occasionally emerged in broader scientific imagination. If Antarctica acts as a long-term collector of extraterrestrial material, could variations in recovery patterns reflect ancient changes in atmospheric entry rates or orbital debris distribution over geological timescales? Could ice dynamics selectively preserve or obscure certain classes of meteorites based on size, composition, or deposition timing? These ideas remain theoretical and are explored only within modeling and hypothesis, not as established conclusions. There is also the simple reality of scale. Antarctica is vast, and its interior remains one of the least densely sampled regions on Earth. Even with modern satellite mapping and coordinated field expeditions, much of the continent remains beyond routine observational coverage. What appears as absence may, in many cases, be absence of access rather than absence of material. And yet, meteorites themselves carry a quiet significance. Each fragment represents material formed beyond Earth, ancient remnants of planetary formation, preserved through time and delivered across space. In Antarctica, they are not only scientific specimens, but also markers of cosmic history resting temporarily on a frozen surface before being collected, studied, and removed. From the scattered fragments of meteorites preserved in Antarctic ice, each one a silent messenger from deep space slowly revealed by moving glaciers, the narrative shifts once more, this time away from what arrives on Earth and toward what is already part of it, yet slowly breaking apart. At the edge of the Antarctic continent, where the interior ice sheet finally meets the open ocean, lies a vast floating platform of frozen water. It extends outward like a pale, suspended world, neither land nor sea, but something in between. This is the region of the Ross Ice Shelf, one of the largest ice formations on Earth, spanning an area comparable to several European countries combined. It appears stable at first glance, a continuous white expanse stretching toward the horizon, interrupted only by pressure ridges, crevasse fields, and distant ice cliffs where the shelf meets the sea. But stability, in this environment, is always temporary. Ice here is not static. It flows, bends, and slowly deforms under its own immense weight. Within this massive frozen platform, scientists have long observed something both expected and unsettling: cracks. These fractures, sometimes subtle and hairline thin, and other times wide enough to form deep chasms, are part of the natural life cycle of ice shelves. They form as the shelf moves outward from the continent, stretching under gravitational forces and interacting with ocean currents from below. As the ice accelerates or encounters variations in thickness, internal stress accumulates. Eventually, that stress is released in the form of crevasses and rifts. Mainstream glaciology describes these processes in mechanical terms: stress distribution, shear zones, basal melting, and ocean-driven undercutting. Warm ocean water can erode the underside of the ice shelf, weakening its structural integrity. Surface melting, though limited in Antarctica's extreme cold, can also contribute to fracture formation. Over time, these factors combine to produce the visible cracks that mark the Ross Ice Shelf. From this perspective, cracks are not anomalies. They are expected features of a dynamic system in motion. And yet, the scale and behavior of some of these fractures invite closer attention. Satellite imagery and aerial surveys have recorded the gradual propagation of major rifts across the ice shelf, some extending for tens or even hundreds of kilometers. These cracks do not always follow simple linear patterns. In certain cases, they branch, curve, or propagate in ways that suggest complex interactions between surface stress, basal conditions, and internal ice structure. One of the most studied features is a series of large rifts that have developed over decades, slowly advancing through the ice like geological fault lines in motion. Scientists monitor these changes carefully, as the behavior of ice shelves plays a critical role in regulating the flow of inland glaciers into the ocean. If a large section were to break away, it would not raise sea levels directly, but it could accelerate the movement of grounded ice behind it, an indirect but significant consequence. Within this framework, cracks in the Ross Ice Shelf are understood as part of a long-term equilibrium process. The ice is constantly adjusting to environmental forces, redistributing stress across its structure in a slow, continuous cycle of deformation and release. But the Antarctic environment often resists simple closure in interpretation. Some observational data has shown that certain fracture patterns evolve in ways that are difficult to fully replicate in models. The timing of rift propagation, the sudden acceleration of crack growth in some regions, and the uneven distribution of structural weakening have led researchers to refine their understanding of how ice shelves respond to combined atmospheric and oceanic forces. The underside of the Ross Ice Shelf, for example, is influenced by ocean currents that flow into subice cavities. These currents carry heat from deeper waters, subtly melting the base of the ice in patterns that are still being mapped. In some areas, this basal melting is uneven, potentially contributing to localized thinning that influences surface cracking above. Still, even with these mechanisms in place, the complexity of fracture behavior remains an active area of study. Could small variations in ocean temperature or salinity create cascading effects in ice stability? Could internal ice layering, formed over thousands of years of snowfall compression, guide cracks along invisible structural boundaries? These are questions that continue to shape glaciological research. Beyond established science, broader speculative reflections occasionally emerge in discussions about Antarctic ice systems, not as assertions, but as thought experiments. If ice shelves act as interfaces between ocean and continent, could they respond to long-term environmental shifts in ways that are not immediately visible on the surface? Could the timing and distribution of cracking reveal deeper cycles of change occurring over centuries rather than decades? These ideas remain within the realm of interpretation and modeling. They do not replace established understanding, but they reflect the inherent difficulty of observing processes that unfold on timescales far beyond a human lifetime. What remains undeniable is the slow motion of the Ross Ice Shelf itself. It is not fixed in place, but continuously drifting outward, carrying its internal structure toward the ocean, where eventual calving events will release massive icebergs into surrounding waters. Each crack, each rift, each subtle shift in the ice is part of that long progression, an unfolding process that began long before human observation and will continue long after. And so, as the exploration moves from meteorites embedded in ancient ice to fractures forming in floating shelves, another question emerges in quiet continuity. When a structure as vast and seemingly stable as the Ross Ice Shelf begins to reveal its internal stresses through growing cracks, are we witnessing simple mechanical adjustment, or the visible surface of deeper, long-term transformations still unfolding beneath Antarctica's frozen edge? From the slow widening fractures of the Ross Ice Shelf, where immense slabs of ice drift toward eventual separation from the Antarctic continent, the narrative turns inward again, away from geological timescales and into a single human story suspended within the same frozen world. At the beginning of the 20th century, when Antarctica was still largely a blank space on global maps, an expedition set out into this same environment with limited knowledge of what lay ahead. The ice was not yet fully measured, the storms not yet fully understood, and survival depended on navigation through a landscape that shifted without warning. This is where the story of Imperial Trans-Antarctic Expedition begins to take shape, an attempt led by Ernest Shackleton to cross Antarctica from sea to sea via the South Pole. The plan was ambitious, even by the standards of the heroic age of Antarctic exploration, to traverse one of the most hostile environments on Earth using sledges, dogs, and endurance alone. The expedition ship, the Endurance, entered the Weddell Sea in 1915, moving through pack ice that appeared at first manageable. But the Antarctic environment does not remain consistent for long. Ice conditions shifted, closing around the vessel. What began as a voyage became a prolonged entrapment. For months, the ship remained frozen in place, held within drifting sea ice that moved slowly with ocean currents. The crew lived aboard as the ice tightened around the hull, creaking and pressing against the wooden structure. Eventually, the pressure became too great. the Endurance was crushed, its timbers bending and breaking under forces no ship of its time could withstand. What followed was not a retreat, but a survival scenario that has since become one of the most studied episodes in polar history. Shackleton and his crew abandoned the sinking vessel, establishing temporary camps on drifting ice floes. They lived on unstable platforms of frozen ocean, aware that the ice beneath them was not fixed ground, but a moving, fragmenting surface that could open or collapse without warning. The Antarctic environment that modern science now studies in detail, the same region where ice shelves crack, polynyas open, and currents reshape frozen boundaries, was experienced directly, without instrumentation or forecast. Mainstream historical accounts emphasize leadership, discipline, and careful decision-making as the core reasons for their survival. Shackleton's navigation of uncertainty, his ability to maintain morale, and the crew's adaptability under extreme conditions are often highlighted as defining elements of the expedition's outcome. After months adrift on the ice, the crew eventually launched lifeboats into open water and navigated through some of the most dangerous seas on Earth to reach Elephant Island. From there, Shackleton undertook an extraordinary open boat journey across the Southern Ocean to South Georgia, seeking rescue for his remaining men. All members of the expedition ultimately survived. And yet, when viewed through the lens of modern Antarctic understanding, the journey acquires additional layers of context. The same environment that trapped the Endurance is now known to be shaped by complex interactions between sea ice dynamics, ocean currents, and atmospheric pressure systems. The Weddell Sea, where the ship became immobilized, is also the region where large polynyas can form, vast openings in sea ice that appear and vanish over time. The ice itself is not static, but constantly in motion, driven by forces that were only partially understood at the time of the expedition. From a scientific perspective, Shackleton's survival can be interpreted as a combination of skill, timing, and environmental conditions that happened to align within a narrow margin of possibility. The stability of ice flows, the availability of open water routes, and the seasonal behavior of sea ice all played roles that modern models attempt to reconstruct in retrospect. But even with detailed reconstructions, there remain aspects of the journey that resist simple compression into data. How did a small group of individuals navigate such a fragmented and shifting environment with no external communication? How did they maintain cohesion across months of uncertainty on moving ice? And how much of their survival depended not only on decision-making, but on environmental conditions that fluctuated in ways they could not possibly predict? In more reflective discussions, the expedition is sometimes viewed as an intersection between human endurance and Antarctic instability, a moment where human presence and natural volatility converged in a uniquely narrow window of survivability. The same ice systems that today are monitored for cracks, flows, and structural changes were the unseen terrain beneath their feet. The wreck of the Endurance itself was rediscovered in recent times, resting on the seabed of the Weddell Sea, remarkably preserved in the cold, dark water. Its condition offers a silent continuation of the story, a physical remnant of a vessel that once moved through ice, now better understood as part of a dynamic and shifting system. And so the narrative does not end with survival alone, but extends into reflection. If the same region that trapped Shackleton's expedition is now known to contain shifting ice shelves, forming cracks, opening polynyas, and interacting with deep ocean currents in ways only recently mapped, then the question becomes less about what happened in the past, and more about how that environment behaves beyond human observation. As the exploration continues through Antarctica's hidden systems, from buried lakes to subglacial heat, from cosmic particles to shifting ice shelves, the story of the Endurance lingers as a reminder of how closely human history is tied to a continent still only partially understood. And so another question quietly remains, echoing across both time and ice. When survival depends so completely on an environment that is constantly in motion, Are we remembering a finished story, or only the first recorded chapter of a landscape that continues to change in ways we are still learning to read? From the drifting ice of the Weddell Sea, where Shackleton's endurance once became locked in a frozen grip and time itself seemed to slow, the narrative returns once more to what lies beneath Antarctica's surface. Not ships this time, not shifting sea ice, but something even more concealed. Water that has never seen light, sealed beneath kilometers of ice for tens of thousands of years. Far beneath the West Antarctic ice sheet, hidden under a continuous blanket of frozen pressure, lies a vast subglacial basin that was unknown to science until modern radar surveys began to reveal irregularities in the ice bed. What appeared at first as subtle distortions in reflection data gradually resolved into something far more structured, a deep, stable body of liquid water, isolated from the surface world for an extended geological time frame. This is Lake Mercer. It sits within a region of Antarctica where the ice is not merely static cover, but a slow-moving system, deforming under its own weight while interacting with the terrain beneath it. Lake Mercer lies buried beneath more than a kilometer of ice, sealed away from sunlight, atmosphere, and direct surface exchange. Unlike surface lakes, it does not freeze solid, despite the extreme cold above it. Instead, it remains in a liquid state due to the immense pressure exerted by the ice above and the geothermal heat rising from Earth's interior. Mainstream scientific interpretation describes Lake Mercer as part of a broader network of subglacial hydrological systems across West Antarctica. Radar and seismic surveys suggest that water beneath the ice sheet is not static, but slowly moves through interconnected channels and basins. In this framework, Lake Mercer is one node in a hidden plumbing system beneath the continent, where water accumulates, drains, and redistributes over long timescales. Its discovery was confirmed in the 2000s through satellite data and ice-penetrating radar, and later studied through carefully controlled drilling missions. When researchers finally reached the lake, they took strict precautions to avoid contamination, using sterile equipment designed to preserve the integrity of the isolated environment. What they encountered was not an empty void, but liquid water containing fine sediment and chemical signatures that suggest long-term interaction with the underlying rock. In many ways, Lake Mercer is now considered a natural laboratory, an extreme environment where scientists can study how isolated aquatic systems behave without sunlight or atmospheric influence. Microbial life has been detected in samples retrieved from similar subglacial lakes, raising the possibility that ecosystems may persist in conditions once thought completely uninhabitable. And yet, even with these advances, Lake Mercer remains only partially understood. One of the central questions concerns its stability. Subglacial lakes are not necessarily permanent features. They can fill and drain over time as ice pressure shifts and meltwater pathways open or close. In some models, Lake Mercer may periodically exchange water with surrounding subglacial systems, creating cycles of accumulation and release that unfold over decades or centuries. But direct observation is extremely limited. Everything known about the lake is inferred from indirect measurements, radar reflections, ice deformation patterns, and carefully extracted samples. The lake itself, in its full volume and structure, remains unseen. There are also broader geological questions tied to its existence. The West Antarctic ice sheet is known to rest on a bed that lies below sea level in many regions, making it particularly sensitive to changes in ocean temperature and ice dynamics. Subglacial lakes like Mercer may play a role in lubricating the base of the ice sheet, influencing how quickly glaciers flow toward the ocean. In this sense, they are not isolated curiosities, but active components of a much larger system. Still, uncertainties remain about how these lakes interact with each other and with the broader ice sheet. Could changes in one subglacial basin affect distant regions through connected drainage pathways? How rapidly can these systems respond to shifts in surface temperature or oceanic intrusion beneath ice shelves? These are questions still being explored through modeling and field data. Beyond established science, Lake Mercer also occupies a place in broader scientific imagination, not as speculation, but as a conceptual boundary. If liquid water can persist in complete isolation for tens of thousands of years, shielded beneath kilometers of ice, what does that imply about the resilience of similar environments elsewhere in the solar system? Subglacial oceans on icy moons, for example, are often compared to systems like Mercer, not because they are identical, but because they share structural parallels: darkness, pressure, and long-term isolation. Yet even within Earth's own boundaries, Lake Mercer remains only partially accessed. Each expedition reveals more detail, but never the full picture. The lake is still too large, too deep, too constrained by ice to be observed in its entirety, and so it remains in a quiet state of partial revelation, a body of water that exists but does not appear in any surface landscape, a system that moves but cannot be directly seen moving, a place that is known through measurement but not through presence. As the exploration continues from ice shelf fractures to subglacial heat, from meteorite fields to buried mountain ranges, Lake Mercer adds another layer to the unfolding picture of Antarctica. Not as a solid, unchanging continent, but as a dynamic system with hidden circulation beneath its frozen exterior. And so a final question emerges, not as conclusion, but as continuation. When entire lakes can exist unseen beneath kilometers of ice, connected to broader systems we are only beginning to map, how much of Antarctica's hidden world is still waiting beneath layers we have not yet learned how to fully interpret? From the dark waters of Lake Mercer, sealed beneath more than a kilometer of ice and hidden from sunlight for millennia, the narrative rises once more toward the surface world, but not toward stillness. Instead, toward motion. Toward life moving across one of the most hostile landscapes on Earth, guided by instincts that still defy complete explanation. At the outer edges of Antarctica, where sea ice meets open ocean and winter darkness stretches for months without interruption, vast colonies gather on floating platforms of frozen sea. Here, in temperatures that can drop far below freezing, life persists not in spite of the environment, but within it. Among the most remarkable of these species is the emperor penguin, the largest of all penguin species, uniquely adapted to survive and reproduce in the heart of the Antarctic winter. Unlike most animals, emperor penguins do not simply endure the Antarctic environment. They actively navigate it across immense distances. During the breeding season, they travel from open ocean feeding grounds to inland colonies located deep on stable sea ice, sometimes covering over 100 kilometers across featureless white terrain with no trees, no landmarks, and no visible directional cues. And yet, year after year, they arrive. Mainstream biology explains this extraordinary navigation through a combination of environmental cues and biological adaptation. Emperor penguins are believed to use a sophisticated integration of sensory information: the position of the sun when visible, subtle gradients in the Earth's magnetic field, the pattern of prevailing winds, and even the angle of polarized light reflecting off ice crystals. Their movement is not random, but guided by a complex internal mapping system shaped by evolution in one of the most stable yet visually uniform environments on Earth. In this interpretation, what appears mysterious is the result of refined biological calibration, an organism tuned over time to read signals invisible to human perception. Still, the precision of their navigation continues to draw scientific attention. In a landscape where visual reference points are nearly absent, even small errors in orientation could lead to fatal consequences. Yet emperor penguins consistently locate breeding colonies with remarkable accuracy, often returning to the same locations across generations. chicks later imprint on these sites, continuing the cycle with similar precision. Field studies have shown that when visual cues are artificially obscured or displaced, penguins may adjust their paths, suggesting a flexible navigation system rather than a single fixed mechanism. But the exact weighting of sensory inputs remains an active area of research. Some studies have explored the role of geomagnetic sensitivity. Like many migratory animals, emperor penguins appear capable of detecting variations in Earth's magnetic field, potentially using it as a directional reference in the absence of visual landmarks. However, the mechanism by which this sensory ability functions at a biological level is still not fully understood. Other research has focused on olfactory cues carried by wind patterns over ice and sea. While Antarctica is often considered a low-odor environment, subtle chemical signals may still play a role in navigation, especially over long distances. And yet, even when all known factors are combined in models, the consistency of penguin migration routes remains difficult to fully replicate. Beyond established biology, broader scientific curiosity occasionally turns toward more abstract questions, not as claims, but as reflections on complexity. How does a brain, evolved for survival in one of the most visually uniform environments on Earth, construct a reliable spatial map across hundreds of kilometers of shifting ice? How does memory interact with environmental feedback in a landscape that changes subtly with wind, temperature, and seasonal ice movement? Could navigation in such extreme environments rely on layers of perception that are not yet fully measured? Or is it simply that current models are still too limited to capture the full integration of known biological systems? What makes Antarctica particularly compelling in this context is its uniformity. A white expanse with few landmarks should, in theory, be disorienting. Yet for emperor penguins, it is navigable. Their journeys suggest a level of environmental reading that transforms an apparently featureless world into a structured, traversable space. Observations from satellite tracking have revealed consistent migration corridors across sea ice, sometimes aligning with subtle environmental gradients that are not visually apparent at ground level. These patterns suggest that what appears flat and uniform to human observers may contain layered signals perceptible to other species. Still, many aspects remain unresolved. Juvenile penguins, making their first journeys, already demonstrate a surprising degree of directional accuracy. Whether this is learned, inherited, or a combination of both remains an open question. Likewise, how environmental changes, such as shifting ice stability or changing magnetic conditions, might affect long-term navigation patterns is still being studied. In this way, emperor penguins become more than a subject of biological interest. They become participants in a larger Antarctic system where movement, ice, magnetism, and survival are deeply interconnected. And so the narrative continues, from hidden subglacial lakes where water has never seen light, to drifting ice shelves that crack under planetary forces, to animals that traverse featureless terrain with uncanny precision. And as the journey follows these paths across the frozen continent, one final question quietly emerges. If navigation itself can emerge from such extreme simplicity of environment, how much of what we consider direction on Earth is still shaped by patterns we have not yet fully learned to perceive? From the precise navigation of emperor penguins across vast, featureless ice, where instinct and subtle environmental cues guide life through one of the most uniform landscapes on Earth, the narrative turns once again beneath the surface, not to animals crossing the ice, but to movement occurring far below it, hidden from sight entirely. Underneath the Antarctic ice sheet, where pressure from kilometers of accumulated snow and ice compresses the continent into a slowly shifting mass, water does not simply freeze in place. Instead, in certain regions, it flows. It carves pathways beneath the ice, following gradients of pressure and heat, forming channels that remain completely invisible from above. These are the subglacial rivers, networks of liquid water that exist beneath the frozen surface of Antarctica, moving silently through a world that has never seen light. At first glance, the idea appears contradictory. Antarctica is defined by cold so extreme that water exposed at the surface freezes almost instantly. And yet, beneath the insulating weight of the ice sheet, conditions are different. The immense pressure lowers the freezing point of water, while geothermal heat rising from the Earth's interior provides just enough energy to maintain pockets of liquid water. Over time, this water does not remain stationary. It begins to move, following the slope of the bedrock beneath the ice, forming slow but persistent flows. Mainstream glaciology describes these systems as part of a broader subglacial hydrological network. Meltwater from the base of the ice sheet accumulates in subglacial lakes, then drains through channels carved into the bedrock or sediment below. These flows can extend for hundreds of kilometers, connecting distant parts of the ice sheet in a hidden circulation system that influences how the ice moves above it. In this framework, subglacial rivers are not anomalies. They are integral components of ice sheet dynamics. They act as lubricants at the base of glaciers, reducing friction and affecting the speed at which ice flows toward the ocean. Satellite data and radar mapping have revealed that these water systems can shift over time, filling and draining in cycles that may occur over years or decades. And yet, despite increasing observational detail, these rivers remain among the least directly observed features on Earth. Everything known about them comes from indirect measurement. Radar echoes that suggest liquid water beneath ice, subtle changes in ice surface elevation, and gravitational anomalies that hint at shifting mass below the surface. No human has ever seen a subglacial river directly in its natural state. Some of the most studied systems are believed to drain large subglacial lakes, such as Lake Vostok and Lake Mercer, transporting water across vast distances beneath the ice sheet. These drainage events can occur suddenly or gradually, reshaping subglacial landscapes in ways that are still being mapped in detail. In some cases, water released from one region may reappear hundreds of kilometers away, suggesting interconnected pathways that span large portions of the continent. From a physical perspective, these rivers are governed by pressure gradients rather than open-air gravity alone. The ice above acts as both a barrier and a driving force, pressing down on the water and influencing its direction of flow. In certain regions, the bed beneath the ice is smooth and deep enough to allow long, continuous channels to form. In others, rough terrain breaks the flow into segmented pathways, creating a complex and dynamic system. Still, the full structure of this network remains incomplete. Radar surveys continue to reveal new channels, some of which appear and disappear over time. In some regions, previously detected water flows have shifted location or become inactive, suggesting a system that is not fixed, but evolving. Beyond established science, broader scientific reflection sometimes turns toward conceptual questions about these hidden rivers. If water can flow beneath kilometers of ice for distances comparable to major surface rivers, what does that imply about the stability and connectivity of subglacial environments? Could these systems influence each other across continental scales? Could changes in one subglacial basin propagate through hidden channels in ways that are not yet fully understood? There is also the question of time. Subglacial rivers operate on timescales that are difficult to observe directly. A flow event may last years, decades, or longer, with subtle shifts occurring far below the threshold of human perception. What appears static from the surface may, in fact, be part of a slow-moving, continuous redistribution of water beneath the ice sheet. In more speculative scientific discussions, always framed cautiously, these systems are sometimes compared to other planetary environments. Subsurface oceans and hidden water channels on icy moons are often studied through the lens of Antarctic subglacial hydrology. Not because they are identical, but because Antarctica offers the closest accessible analog to such environments on Earth. Yet even within this comparative framework, the Antarctic system itself remains only partially mapped. There are still vast regions where bed conditions are inferred rather than measured. There are still uncertainties about how quickly water can move through subglacial channels, how often drainage systems reorganize, and how deeply they interact with the overlying ice dynamics. And so the image that emerges is not one of a single river, but of an entire hidden hydrological system, fluid, shifting, and largely unseen, operating beneath a continent that appears frozen and still from above. As the exploration continues from surface navigation by emperor penguins to buried lakes, cracking ice shelves, and now flowing water beneath kilometers of ice, a deeper pattern begins to take shape. Antarctica is not a static block of ice, but a layered system of movement, exchange, and transformation occurring on multiple levels simultaneously. And so another question arises, quietly and without resolution. When entire river systems can flow unseen beneath one of the most extreme ice sheets on Earth, how much of Antarctica's internal circulation is still waiting to be mapped, understood, or even discovered for the first time? From the unseen rivers flowing beneath kilometers of Antarctic ice, where liquid water moves in silence through a buried landscape, the narrative rises once more to the surface of the ocean, but not toward calm seas. Instead, toward one of the most unpredictable and violent environments on Earth. Beyond the ice edge of Antarctica lies a vast, encircling body of water that separates the frozen continent from the rest of the world's oceans. This is the region of the Southern Ocean, a continuous, powerful system driven by some of the strongest winds and currents on the planet. It is here that the Antarctic circumpolar current flows uninterrupted around the globe, carrying energy, temperature gradients, and immense volumes of water without obstruction from continents. In this remote and storm-prone environment, waves behave differently. Among the most striking and least predictable phenomena observed here are what oceanographers call rogue waves, sudden, isolated walls of water that rise far above surrounding sea states, appearing briefly before collapsing back into the ocean surface. These are known as rogue waves. Unlike regular waves, which follow relatively predictable patterns based on wind speed, fetch, and ocean depth, rogue waves are defined by their disproportionate height and sudden emergence. They can appear in otherwise moderate sea conditions, rising without warning and dissipating just as quickly. In the Southern Ocean, where storms are frequent and wave systems are already powerful, these extreme events become even more difficult to isolate and study. Mainstream oceanography explains rogue waves through a combination of well-understood physical processes. Constructive interference between wave systems can temporarily amplify wave height. Strong currents interacting with opposing wind-driven waves can compress wave energy into localized peaks. Nonlinear wave dynamics, where energy is transferred unpredictably between wave groups, can also produce rare but extreme outliers. In this framework, rogue waves are not violations of physics, but rare expressions of it under specific and overlapping conditions. And yet, the Southern Ocean is not a typical environment. It is a continuous belt of open water encircling Antarctica, largely unbroken by land masses. This allows wave energy to travel vast distances uninterrupted, building momentum across thousands of kilometers. Storm systems in this region can persist and intensify, feeding into each other in ways that create highly complex sea states. The result is an ocean where multiple wave systems coexist, overlap, and interact constantly. In such conditions, even well-modeled predictions become probabilistic rather than precise. Ships traversing these waters have reported encounters with waves that seem to rise faster and steeper than surrounding models would suggest. Satellite measurements and buoy data have confirmed that extreme wave events do occur more frequently here than in many other parts of the world's oceans. However, capturing them in real time remains challenging due to their unpredictability and short duration. Some of the most studied rogue wave events in the Southern Ocean have occurred during intense storm systems where multiple wave trains intersect. In these situations, energy can become temporarily focused, producing a wave that stands significantly above the surrounding sea state before dispersing. Yet even with this understanding, the statistical nature of these events leaves room for continued investigation. Why do certain regions of the Southern Ocean appear to generate extreme wave activity more frequently than others under similar conditions? How do long-range wave interactions across the circumpolar current influence local sea states? And what role, if any, do shifting climate patterns play in altering the frequency or intensity of these events? The Southern Ocean is also uniquely sensitive to global atmospheric dynamics. It acts as a major connector between ocean basins, transferring heat and momentum around the planet. This makes it not only a region of extreme weather, but also a key component in global climate systems. Subtle changes in wind patterns or ocean temperature can propagate through this system, potentially influencing wave behavior in ways that are still being actively studied. Beyond established models, some oceanographers have explored more abstract considerations, not as definitive explanations, but as attempts to describe complexity at scale. Could the interaction of multiple long-period wave systems across such an uninterrupted ocean belt produce rare, nonlinear events more frequently than expected? Could energy accumulation across vast distances contribute to localized amplifications that appear sudden only from a limited observational perspective? These questions remain within the boundaries of physical theory, but they highlight the difficulty of fully capturing a system as large and dynamic as the Southern Ocean. What makes rogue waves particularly compelling is not only their size, but their unpredictability. Even with modern satellite monitoring and numerical modeling, they resist precise forecasting. They exist at the intersection of known physics and probabilistic extremes, events that are rare but not impossible, and therefore difficult to fully anticipate. In this sense, the Southern Ocean becomes more than just a body of water surrounding Antarctica. It becomes a vast, interconnected energy system, where waves generated on one side of the globe can eventually influence conditions on another, where storms merge and disperse, and where extreme events occasionally emerge from the interaction of countless variables. And so the image remains, a remote, encircling ocean where waves travel without interruption, gathering energy across immense distances before occasionally rising into forms that challenge expectation. As the exploration continues from subglacial rivers beneath the ice to drifting ice shelves, from hidden lakes and buried mountains to the movement of life across the surface, the Southern Ocean adds another dimension to the Antarctic system, one defined not by stillness, but by relentless motion. And as the waves continue their endless circulation around the frozen continent, another question quietly emerges. In a system where energy travels freely across thousands of kilometers of open water, how many of the ocean's most extreme events are still unfolding beyond the limits of continuous observation? From the towering, unpredictable forces of the Southern Ocean, where rogue waves rise without warning and travel across vast distances of open water, the narrative shifts once more toward the Antarctic coastline itself. Here, the ocean's motion meets the stillness of ice, and in that fragile boundary between liquid and frozen worlds, something unusual has been observed. Not the blue-white uniformity of snow that defines most Antarctic landscapes, but a subtle transformation of color, a faint tint spreading across otherwise pristine surfaces. At first glance, it appears almost unreal, like a visual distortion against the overwhelming whiteness of the continent. This is the phenomenon known as green snow. It has been documented in several coastal and maritime regions of Antarctica, where seasonal changes, melt conditions, and biological activity occasionally converge in ways that alter the appearance of the snowpack. From a distance, the affected areas can appear as if the ice itself has been lightly stained, as though the surface of the continent is responding to something invisible within or above it. Mainstream scientific explanations begin with biology. In many documented cases, green or greenish snow is associated with the presence of microscopic algae, particularly snow algae that thrive in cold environments during brief Antarctic summer periods. When conditions allow for slight melting and increased sunlight, these organisms can bloom within the upper layers of snow. Their pigmentation, often rich in chlorophyll and other protective compounds, can tint the surrounding snow surface, producing a greenish hue when observed at scale. In this framework, the phenomenon is not only natural, but expected under specific environmental conditions. The Antarctic ecosystem, though extreme, is not biologically inactive. Microorganisms, extremophiles, and cold-adapted algae can persist in niches where liquid water is briefly available. When sunlight returns after the long polar night, even minimal biological activity can become visible across large areas due to the reflective nature of snow. Yet even within this biological explanation, the phenomenon raises deeper questions about scale and distribution. Why do these blooms appear in certain regions and not others with seemingly similar conditions? Why does the coloration sometimes form in patches, gradients, or irregular patterns rather than uniform spreads? And how do these microscopic organisms survive the prolonged darkness and freezing conditions that dominate much of the Antarctic year? Field studies suggest that snow algae can enter dormant states, surviving long periods of cold and darkness before reactivating when conditions improve. Their life cycle is tightly coupled to seasonal melt cycles, nutrient availability, and moisture levels within the snowpack. In this sense, green snow is not an anomaly, but a visible expression of microbial adaptation to extreme environments. However, the Antarctic environment is rarely governed by a single factor. In coastal regions, wind-blown dust, mineral particles, and ocean-derived aerosols can interact with snow surfaces. These inputs may influence nutrient availability, potentially supporting localized biological growth. Subtle variations in salinity or trace minerals deposited through atmospheric circulation can also affect microbial activity in ways that are still being studied. This interconnectedness between ocean, atmosphere, and ice becomes particularly significant when considering the broader Antarctic system. The same Southern Ocean that generates rogue waves and drives powerful circumpolar currents also contributes moisture, aerosols, and nutrients to the continent's edges. Even distant oceanic processes can indirectly influence what appears on the surface of Antarctic snow. From this perspective, green snow becomes part of a larger environmental network, a visible outcome of interactions between marine systems, atmospheric transport, and cryospheric conditions. And yet, even with these explanations, the phenomenon continues to invite closer observation. Satellite imagery has occasionally captured areas of discolored snow extending over broad regions, with subtle variations in tone and intensity. While many of these patterns are consistent with biological growth, the complexity of their distribution sometimes requires detailed field validation to fully interpret. Researchers working in coastal Antarctic stations have also noted that snow coloration can change rapidly over short timescales, sometimes shifting in response to temperature fluctuations, wind events, or brief melt periods. This dynamic behavior suggests that the system is not static, but responsive to a combination of environmental triggers. Beyond established scientific interpretation, broader questions occasionally arise in discussions of polar ecosystems, not as conclusions, but as reflections on complexity. Could microbial life in extreme environments like Antarctica be more widespread beneath the surface than current sampling reveals? Could subsurface melt layers or thin liquid films within snowpacks support microbial activity even outside typical melt seasons? And how might long-term climate variability influence the distribution and visibility of these biological systems? These questions remain within the boundaries of active research, approached through microbiology, climatology, and glaciology. They do not suggest unknown forces, but rather emphasize how much of the cryosphere remains only partially sampled at microscopic scales. What makes green snow particularly compelling is not its color alone, but what it represents. A moment where life, even in its smallest forms, becomes visible against one of the most extreme environments on Earth. A continent defined by cold and isolation briefly reveals signs of biological presence, not through movement or sound, but through pigment carried across frozen surfaces. And yet, even this visibility is temporary. As temperatures drop or conditions shift, the snow returns to its uniform state, and the green fades back into the overwhelming white that dominates the Antarctic landscape. This transient nature raises its own quiet questions. How many such biological events occur unnoticed beneath or within the snow each year? How much microbial activity remains hidden in layers too thin, too brief, or too remote to be easily observed? And what does it mean for our understanding of life in extreme environments if such processes are both widespread and fleeting? As the exploration continues, from hidden subglacial rivers to cracking ice shelves, from deep ocean rogue waves to penguin navigation across featureless ice, the green snow phenomenon adds another layer to the Antarctic narrative. Not one of geology or physics alone, but of life persisting in delicate, transient expression across a frozen continent. And so the image lingers, a vast white expanse, seemingly still and uniform, occasionally touched by faint traces of green, temporary signatures of microscopic systems responding to a world in constant, subtle motion beneath the surface. And as the continent continues its slow seasonal cycles, another question quietly remains in the background. In a place where life is so finely balanced between dormancy and activity, how many biological processes are unfolding across Antarctica right now, visible only for a moment, before returning once again into the silence of the ice? From the faint green tint of Antarctic snow, where microscopic life briefly reveals itself in fleeting seasonal cycles, the narrative turns away from the visible surface once again. This time, it moves backward in time, into one of the earliest and most psychologically unsettling human encounters with the frozen continent. Before radar mapped subglacial lakes, before satellites revealed hidden mountain ranges beneath the ice, and before modern expeditions decoded the dynamics of ice shelves and ocean currents, Antarctica was still largely unknown. Expeditions ventured into it not with data, but with uncertainty. Among the earliest and most haunting of these journeys was a voyage that would later become one of the most studied psychological cases in polar exploration. This is the story of the Belgica expedition. Led by Adrien de Gerlache aboard the ship Belgica, the expedition set out with scientific ambition, aiming to explore uncharted Antarctic waters and conduct early research in a region still barely understood by modern science of the time. The crew included a multinational team of scientists and sailors, among them figures such as Roald Amundsen and Frederick Cook, who would later become central to polar exploration history. At first, the voyage progressed as planned. The ship entered Antarctic waters, navigating ice-filled seas that were already known to be unpredictable. But as winter approached, the situation changed dramatically. The Belgica became trapped in sea ice in the Bellingshausen Sea, unable to break free. Unlike planned overwintering expeditions, this was not an intended pause. It was an enforced isolation. As the Antarctic winter deepened, the crew found themselves in a world where daylight disappeared entirely for months. The ship became locked in a drifting ice field, surrounded by a vast, silent landscape of frozen pressure ridges and shifting white horizons. Time lost its usual structure. The environment no longer changed in visible ways. The horizon remained constant, and the ice held everything in place. What followed has been described in historical accounts as one of the earliest documented cases of what would later be understood as polar madness, a psychological and physiological deterioration observed in individuals subjected to prolonged isolation, darkness, and environmental monotony. Mainstream historical and medical interpretation attributes these effects to a combination of factors: vitamin deficiencies, particularly scurvy, disrupted circadian rhythms due to prolonged darkness, extreme isolation, and nutritional stress. The absence of sunlight for extended periods affects human hormonal cycles, particularly melatonin regulation, which in turn influences sleep, mood, and cognitive stability. Inadequate nutrition further exacerbates physical and psychological strain. Within this framework, the experiences aboard the Belgica are understood as the result of extreme environmental stress acting on the human body and mind under conditions for which it was never adapted. But historical diaries and expedition logs reveal something more complex than simple physiological decline. Crew members reported persistent insomnia, hallucinations, and altered perception of time. Some described auditory sensations, sounds that seemed to come from the ice itself or from beneath the ship, despite the surrounding silence. Others recorded emotional detachment, confusion, and an increasing sense of unreality as the polar night progressed. The Antarctic environment itself played a central role in this psychological transformation. Without visual change, the brain loses external reference points that help structure time and orientation. The drifting ice added another layer of instability. The ship was not anchored to land, but embedded in a moving frozen sea, shifting imperceptibly over time. There was no fixed horizon, no reliable marker of position or progress. Even today, scientists studying Antarctic psychology note that sensory deprivation in polar environments can produce profound cognitive effects. The combination of monotony, darkness, and isolation creates conditions where perception becomes increasingly self-referential. The brain, deprived of external variation, begins to generate internal stimuli. And yet, within the accounts of the Belgica expedition, there are descriptions that continue to draw careful attention. Some entries mention sounds beneath the ice that were difficult to identify. Others describe a growing sense of temporal distortion, where days and nights became indistinguishable even when measured. The crew reportedly struggled not only with physical survival, but with maintaining a shared sense of reality. Modern interpretations emphasize that such experiences are consistent with known effects of polar overwintering in extreme conditions. Yet the psychological intensity described in early Antarctic expeditions like Belgica remains striking, especially given the limited understanding of such environments at the time. Beyond established science and history, broader reflections occasionally emerge in discussions of polar exploration, not as claims, but as questions about human perception under extreme environmental isolation. How does the mind reconstruct reality when external cues disappear almost entirely? How much of perception depends on environmental variation, and what happens when that variation is removed for months at a time? In Antarctica, where light itself disappears for half the year in some regions, these questions are not theoretical. They are lived experiences. The Belgica eventually escaped the ice in 1899, becoming the first expedition to overwinter in Antarctic waters and return successfully. The ship's survival was seen as a triumph of endurance and leadership under extreme conditions. Yet the psychological records left behind remain some of the earliest systematic accounts of human mental adaptation and breakdown in polar isolation. In retrospect, the expedition occupies a unique place in Antarctic history. It sits at the intersection of exploration and psychology, where environmental forces begin to shape not only physical survival, but perception itself. And so, as the narrative continues, from microbial life in green snow, to hidden rivers beneath ice sheets, to oceans that generate rogue waves, and now to the fragile stability of the human mind in polar night, another question quietly emerges. When humans enter environments where time, light, and sensory structure dissolve into near uniformity, how much of what is experienced belongs to the world itself, and how much is created within the mind trying to interpret it? From the psychological disorientation experienced aboard the Belgica, where isolation, darkness, and silence reshaped perception itself, the narrative drifts once more back to the ice. But this time, not to what is seen on its surface, nor what lies beneath it in liquid form. Instead, to something even less visible, yet widely reported across Antarctic research stations, sound without an obvious source. In a continent defined by silence, where wind and ice dominate the acoustic landscape, there are moments when that silence is interrupted in unexpected ways. Not by storms, not by cracking glaciers, but by a low-frequency presence that seems to emerge from the ice itself. This phenomenon is often referred to as Antarctic Ice Humming. It is not a melody in any conventional sense. It is not rhythmic or musical in the human understanding of sound. Instead, it is described as a continuous, low-frequency vibration, sometimes steady, sometimes fluctuating, perceived through instruments and, on rare occasions, faintly detectable by human hearing in extremely quiet conditions. The Antarctic ice sheet is one of the largest and most dynamic cryospheric systems on Earth. It is not static, but in constant motion, flowing slowly under its own weight, deforming over time, interacting with bedrock, ocean currents, and atmospheric forces. Within this system, sound is generated through multiple physical processes. Mainstream glaciology explains ice-related acoustic phenomena as the result of environmental and mechanical activity. Wind passing over sastrugi, sharp ridges formed by wind erosion, can produce tonal vibrations. Temperature changes cause ice to expand and contract, generating stress waves. Ocean swell interacting with ice shelves can transmit low-frequency energy into the ice sheet. Even internal ice movement, as glaciers grind slowly over bedrock, can produce seismic and acoustic signals. In this framework, what is described as ice humming is not a single phenomenon, but a composite of multiple natural processes producing low-frequency vibrations that can be detected by sensitive instruments. Yet what makes Antarctic ice acoustics particularly intriguing is not just that these sounds exist, but how they behave across space and time. Seismometers placed across different parts of the continent have recorded persistent background vibrations that do not always correlate directly with surface weather conditions. In some cases, signals appear to intensify during periods of high wind activity. In others, they persist even during relatively calm atmospheric conditions. These signals are often within the infrasonic range, below the threshold of human hearing, but can be converted into audible sound for analysis. When translated, these recordings sometimes resemble a shifting, undulating tone, steady in presence, but variable in structure. Researchers studying these signals emphasize that Antarctica is acoustically active on a planetary scale. Ice sheets respond to tidal forces, atmospheric pressure changes, and oceanic interactions. The grounding lines of glaciers, the points where ice transitions from land to floating ice shelves, are particularly dynamic regions where mechanical stress can generate continuous micro-vibrations. From a geophysical perspective, the ice sheet can be understood as a massive, slowly deforming medium that constantly emits energy as it adjusts to environmental forces. In this sense, the humming is not an anomaly, but an expected outcome of a system in motion. And yet, even with this understanding, the experience of these sounds can be disorienting. Field researchers stationed in Antarctica have occasionally reported moments where the acoustic environment seems unusually uniform or persistent, as though the entire ice sheet were resonating at once. In remote locations far from human infrastructure, where mechanical noise is absent, the ambient soundscape can feel unusually present, even when nothing obvious is producing it. This perception is not considered unusual in extreme environments. The human auditory system is highly sensitive to low-frequency vibrations, and in quiet conditions, the brain can amplify subtle background signals. Still, the subjective experience of continuous, low-level sound in an environment visually defined by stillness has led to sustained scientific curiosity. Some studies suggest that ice sheets may behave in ways analogous to large resonating systems. Internal fractures, basal sliding, and the interaction between ice and underlying geology can all produce vibrations that propagate over long distances. These signals can overlap, interfere, and combine, creating complex acoustic patterns that vary depending on location and environmental conditions. In coastal regions, where ice shelves interact with ocean waves, additional acoustic inputs are introduced. Ocean swell can transmit energy into ice structures, generating low-frequency vibrations that travel inland. These interactions can persist even when surface conditions appear calm, suggesting that much of the acoustic activity in Antarctica originates beneath or beyond direct visual observation. Beyond established geophysics, broader interpretive questions sometimes arise in discussions of polar acoustics, not as alternative explanations, but as attempts to understand complexity at scale. When a system as vast as the Antarctic ice sheet is continuously deforming, interacting with ocean currents, atmospheric pressure systems, and geothermal heat, how should its collective acoustic output be conceptualized? Is it simply a sum of localized processes, or does it represent a broader integrated response of the entire cryospheric system? Some researchers describe this in purely mechanical terms, a distributed network of stress and strain producing continuous microseismic activity. Others frame it as an emergent property of large-scale ice dynamics, where individual events cannot fully explain the overall acoustic signature. What remains consistent across interpretations is that Antarctica is not silent. Its ice is active, responsive, and continuously adjusting to internal and external forces. Even in the absence of storms or visible movement, the continent produces measurable signals, subtle, persistent, and widespread. And yet, these signals are still only partially mapped. Seismometers and hydrophones provide snapshots of activity at specific locations, but the full spatial and temporal structure of Antarctic acoustic emissions remains incomplete. Vast regions of the interior remain under-instrumented, leaving large gaps in observational coverage. This limitation leaves room for continued exploration. Could variations in ice thickness, temperature gradients, or basal conditions create distinct acoustic signatures that differ across regions? Could long-term monitoring reveal patterns in ice dynamics not yet visible through satellite imagery alone? And how might these signals change as the Antarctic environment responds to ongoing climatic shifts? In this way, ice humming becomes more than an isolated curiosity. It becomes part of a broader attempt to understand Antarctica as a dynamic, multi-layered system, one that communicates its internal processes not through visible motion alone, but through subtle vibrations that propagate through ice, rock, and water. As the narrative continues, from psychological distortion in polar night, to biological signals in green snow, to hidden rivers, drifting ice shelves, and deep ocean waves, the acoustic dimension adds another layer, a reminder that even in apparent stillness, the Antarctic environment is continuously active. And so the question remains, carried not in sound itself, but in its interpretation. When a continent of ice produces a persistent, low-frequency presence that spans vast distances and multiple physical systems, Are we hearing separate events occurring simultaneously, or a single, interconnected signal of a planet still in motion beneath its frozen surface? From the low, continuous acoustic hum of Antarctic ice, where the frozen continent seems to vibrate with processes too vast and subtle to see, the narrative shifts upward, beyond the ice sheet, into the atmosphere itself. Not toward land, not toward ocean, but toward the thin, invisible layer that separates Earth from space. High above Antarctica, where stratospheric winds circulate in powerful, circular patterns around the pole, there exists a region that once represented one of the most dramatic environmental disruptions ever recorded in modern atmospheric science. It is not a feature of the ice below, but of the air above it, a seasonal thinning and depletion of a critical protective layer. This is the region associated with the Antarctic ozone hole. It is not a permanent hole in the physical sense, but a severe seasonal reduction in ozone concentration within the stratosphere, typically occurring during the Antarctic spring. Ozone in this layer plays a crucial role in absorbing ultraviolet radiation from the sun, shielding biological systems on Earth's surface from high-energy UV exposure. The phenomenon first came to global scientific attention in the 1980s, when atmospheric measurements revealed a dramatic and unexpected decline in ozone levels over Antarctica. Subsequent research linked this depletion primarily to human-produced chlorofluorocarbons, CFCs, which, once released into the atmosphere, eventually reach the stratosphere and break down under ultraviolet radiation. This process releases chlorine atoms that catalytically destroy ozone molecules. The discovery led to one of the most significant international environmental agreements in modern history, the Montreal Protocol, which phased out many ozone-depleting substances globally. Over time, observations have shown gradual signs of recovery, with some stabilization and partial rebuilding of ozone concentrations in affected regions. From a scientific perspective, the Antarctic ozone hole is now understood as a coupled chemical and atmospheric dynamics problem. Extremely cold stratospheric temperatures over Antarctica during winter lead to the formation of polar stratospheric clouds. These clouds provide surfaces for chemical reactions that convert relatively inert chlorine compounds into reactive forms. When sunlight returns in spring, these reactive compounds rapidly destroy ozone molecules, leading to a seasonal depletion cycle. In this framework, the hole is not static, but seasonal, shaped by a combination of atmospheric chemistry, temperature, and polar vortex dynamics. And yet, the behavior of this system continues to be closely monitored. Satellite data and ground-based measurements have shown that the size and severity of the ozone hole can vary significantly from year to year. Some seasons exhibit deeper depletion and larger affected areas, while others show more moderate conditions. These fluctuations are influenced by stratospheric temperature variations, volcanic activity, and long-term changes in atmospheric composition. The observed trend toward gradual recovery is considered one of the clearest examples of successful global environmental intervention. However, this recovery is not linear. It is modulated by natural variability in atmospheric circulation, including the strength and stability of the polar vortex, a high-altitude wind system that isolates Antarctic air from lower latitudes. When the polar vortex is strong and stable, conditions favor more extensive ozone depletion. When it weakens or becomes disrupted, mixing with surrounding air can reduce the severity of depletion events. Still, even with this understanding, the system remains complex. Some years have produced unexpected variations in ozone levels that require detailed analysis to fully interpret. Sudden stratospheric warming events, shifts in planetary wave activity, and interactions with lower atmospheric conditions can all influence the structure and evolution of the ozone layer over Antarctica. Beyond the established chemical and physical explanations, the ozone hole has also become a subject of broader reflection within atmospheric science, not in terms of mystery in the unknown sense, but in terms of system complexity and interdependence. The stratosphere is not isolated. It interacts with the troposphere below and the mesosphere above, forming part of a continuous atmospheric system driven by solar radiation, Earth's rotation, and chemical composition. Changes in one layer can propagate through others, sometimes in subtle and delayed ways. In this context, the Antarctic ozone hole is not an isolated phenomenon, but a visible manifestation of global atmospheric connectivity. It also raises deeper questions about sensitivity. Why does such a dramatic depletion occur specifically over Antarctica? The answer lies in the unique conditions of the polar environment: extreme cold, strong seasonal isolation by the polar vortex, and the presence of stratospheric clouds that facilitate chemical reactions not as prevalent elsewhere. But even with these explanations, Antarctica continues to act as a kind of atmospheric amplifier, where global processes become sharply visible due to local conditions. As recovery continues, scientists carefully monitor whether the system is returning to pre-1980 conditions or stabilizing at a new equilibrium influenced by residual greenhouse gases, long-lived atmospheric compounds, and ongoing climate variability. There is also the question of timescales. While chemical recovery of ozone is underway, full restoration is expected to take decades. This slow pace reflects the long atmospheric lifetimes of certain compounds and the inertia of large-scale atmospheric circulation patterns. In the background of this recovery, Antarctica remains a key observational region. Its atmospheric clarity and relative isolation make it one of the most important locations on Earth for monitoring stratospheric changes. Instruments placed on the ice sheet continue to collect data that contribute to global models of ozone dynamics and atmospheric chemistry. And yet, even as measurements improve, the system remains inherently dynamic. The Antarctic atmosphere does not behave as a simple layer of uniform chemistry. It is a shifting, reactive environment influenced by solar cycles, volcanic aerosols, ocean-atmosphere interactions, and long-range transport of gases. Each of these components interacts in ways that are still being refined within predictive models. In some interpretations, the ozone layer becomes a kind of atmospheric memory, recording the cumulative effects of both natural variability and human influence over time. Its gradual recovery is therefore not just a chemical process, but a reflection of changing global conditions. And so, as the narrative continues across Antarctica's hidden systems, from subglacial rivers and buried lakes to drifting ice shelves, ocean waves, ice acoustics, and now the upper atmosphere, another layer is added to the unfolding structure of the continent. A structure that is not only frozen in ice or carved in rock, but suspended in air, shaped by invisible chemistry and planetary motion. And the question that remains, drifting above the ice and into the stratosphere, is this: when a protective layer of the atmosphere begins to heal after decades of disruption, how much of what we observe is a return to balance, and how much is the beginning of a new atmospheric state we are only just learning to recognize? From the slowly recovering Antarctic ozone layer, where atmospheric chemistry is still recalibrating itself after decades of disruption, the narrative descends once more toward the frozen surface below. The stratosphere may be mending in measurable ways, but beneath it, Antarctica remains a continent of constant transformation, where stability is always temporary and silence often hides movement. And now, the focus shifts not to air or ice alone, but to the boundary where both begin to interact in subtle, persistent ways. High above the Antarctic plateau, wind systems continue to circulate with planetary-scale consistency, shaping temperature gradients and influencing the behavior of everything below. These winds do not simply pass over the continent, they define it. They carve patterns into snow, influence ice accumulation, and indirectly contribute to processes occurring deep beneath the surface. It is within this interconnected system that researchers have observed another layer of complexity: the way atmospheric recovery and surface stability are not always synchronized. Even as the ozone layer shows gradual signs of rebuilding, the Antarctic surface continues to respond to longer-term climate and cryospheric shifts. Ice shelves still fracture. Subglacial systems still flow. Ocean currents still press against the continent's edges. Nothing here exists in isolation. And so a broader question begins to emerge. What does recovery mean in a system where every layer is connected? In atmospheric science, recovery of the Antarctic ozone hole is measured through chemical concentration trends, satellite observations, and long-term modeling of stratospheric behavior. These measurements show encouraging signs: a slow reduction in the severity and size of seasonal depletion, particularly during stable atmospheric years. But Antarctica does not respond to a single variable. Below the atmosphere lies a continent still adjusting to shifting energy balances. Ice sheets continue their slow movement toward the ocean. Subglacial rivers adjust their pathways. Ice shelves respond to mechanical stress. The Southern Ocean continues to redistribute heat across hemispheric scales. Each system interacts with the others, sometimes subtly, sometimes dramatically. This raises an important scientific consideration. Even when one component of the Earth system begins to stabilize, the broader system may still be in transition. In climate dynamics, this is often referred to as delayed response or system inertia. The atmosphere may respond relatively quickly to reductions in ozone-depleting substances, but ice sheets and ocean systems operate on far longer timescales. Their responses can unfold over decades or centuries, gradually revealing the full consequences of earlier atmospheric conditions. In Antarctica, this temporal mismatch becomes especially visible. For example, while stratospheric chemistry shows improvement, ice loss patterns in parts of West Antarctica continue to reflect warming trends from previous decades. Ocean-driven melting beneath ice shelves persists due to heat already stored in deep currents. These processes do not immediately reverse, even as atmospheric composition improves. And so the continent becomes a layered archive of different timelines, each system responding at its own pace. This is where scientific observation becomes particularly complex. Researchers must separate short-term variability from long-term trends, distinguishing between seasonal fluctuations and structural change. Satellite data provides broad coverage, but ground measurements remain essential for understanding local dynamics. Yet even with increasingly sophisticated monitoring, Antarctica retains a degree of unpredictability. Some years show unexpected atmospheric stability. Others reveal sudden variability in stratospheric conditions. Similarly, ice behavior can shift in ways that are not fully captured by existing models. These variations do not contradict scientific understanding, but they emphasize the limits of predictability in a system of such scale and interconnection. Within this context, the ozone layer becomes more than a discrete atmospheric feature. It becomes part of a broader planetary feedback system, one that reflects both human influence and natural variability. The gradual reduction in ozone depletion is widely regarded as one of the most successful examples of coordinated global environmental action. The phase-out of chlorofluorocarbons under international agreements demonstrated that atmospheric systems can respond positively to large-scale policy changes. However, the recovery process also highlights the slow nature of atmospheric restoration. Even after emissions are reduced, the remnants of long-lived compounds persist in circulation. Their effects diminish over time, but not instantly. This lag is a defining characteristic of atmospheric chemistry, and yet Antarctica continues to function as a sensitive indicator of these changes. Its position at the southern pole makes it uniquely responsive to stratospheric dynamics. The polar vortex isolates air masses, allowing chemical processes to unfold with limited external interference. As a result, changes in ozone concentration become particularly visible here before being fully apparent elsewhere. This sensitivity turns Antarctica into more than a geographic region. It becomes a diagnostic environment for planetary systems. And so, as the narrative moves across ice, ocean, atmosphere, and time, a pattern begins to form. Each Antarctic phenomenon, whether biological, geological, acoustic, or atmospheric, is part of a larger interconnected structure. From green snow signaling microbial activity, to subglacial rivers reshaping ice from below, to rogue waves transferring energy across hemispheres, to atmospheric recovery unfolding above, all layers are engaged in continuous exchange. Nothing is truly isolated. Even recovery, it seems, is not a single event, but a multi-layered process unfolding at different speeds across different systems. And as this exploration continues, one final question emerges, suspended between sky and ice. If Antarctica is simultaneously responding to changes above it in the atmosphere and below it in the ocean and bedrock, then what does recovery actually look like in a place where every layer is still in motion, and where equilibrium itself may be something that is always approached but never fully reached? From the delicate balance of Antarctic atmospheric recovery, where the ozone layer slowly rebuilds itself in the stratosphere after decades of disruption, the narrative now descends again toward the surface of the continent. But this time, not into ice or air alone. Instead, into a place where rock, salt, and liquid water converge in one of the most visually striking and geochemically unusual environments on Earth. Far from the open ocean and deep within the McMurdo region of Antarctica lies a cold, arid landscape shaped by volcanic geology and extreme polar conditions. Here, within the icy expanse of the McMurdo Dry Valleys, there exists a feature that has drawn scientific attention for more than a century. A flow of water that appears, at times, almost unnatural in color. This is the site associated with the phenomenon known as blood falls. At first glance, it seems almost impossible. In a region where temperatures remain far below freezing for most of the year, a cascade of deep red liquid emerges intermittently from the face of Taylor Glacier, staining the surrounding ice with a color reminiscent of rust or oxidized metal. The effect is visually arresting, a bright, almost surreal contrast between the white glacier and the dark crimson flow that seeps outward before freezing in place. For early observers, the appearance was difficult to interpret. But modern science has provided a detailed explanation rooted in geology, chemistry, and microbial activity. Mainstream understanding identifies blood falls as the outflow of a subglacial hypersaline brine system trapped beneath Taylor Glacier. This brine is highly concentrated with dissolved salts, particularly iron-rich compounds. Because of its extreme salinity, the water remains liquid even at temperatures well below the freezing point of fresh water. Over time, it has become isolated beneath the glacier, forming a sealed subglacial reservoir. When pressure forces small amounts of this brine to the surface, it comes into contact with oxygen in the atmosphere. The iron within the water rapidly oxidizes, producing the characteristic red coloration that gives blood falls its name. In this interpretation, the phenomenon is not only natural but chemically predictable. A combination of hypersaline water, iron-rich sediments, and oxidation processes occurring at the interface between subglacial and atmospheric environments. But the system behind it is far more complex than its striking appearance suggests. The brine reservoir feeding blood falls is believed to have been isolated for hundreds of thousands of years, trapped beneath ice that has remained largely stable over geological time. Within this isolated environment, scientists have discovered microbial life forms adapted to extreme conditions, organisms capable of surviving without sunlight, relying instead on chemical energy derived from dissolved minerals in the brine. These extremophiles provide important insights into how life can persist in environments once thought entirely uninhabitable. Their metabolic processes are slow, highly specialized, and dependent on chemical gradients rather than solar energy. Yet even with this understanding, Bloodfalls continues to raise deeper questions about subglacial systems in Antarctica. One of the most intriguing aspects is the stability of the reservoir itself. The water beneath Taylor Glacier is not static. It is part of a larger subglacial hydrological system, influenced by pressure from overlying ice, geothermal heat from below, and the structural dynamics of the glacier above. In some cases, the flow of brine to the surface appears intermittent, suggesting that internal pressure thresholds must be reached before release occurs. This raises questions about how subglacial systems regulate themselves over time. What controls the timing of these outflows? How do pressure changes propagate through such an isolated reservoir? And how stable are these systems over long geological periods? Geophysical surveys suggest that the subglacial basin feeding Bloodfalls is connected to a broader network of brine channels beneath the Taylor Glacier region. These channels may extend over significant distances, forming a hidden hydrological system that exists entirely beneath the ice sheet. From a physical standpoint, this system is governed by pressure gradients, salinity-driven density differences, and the thermal insulation provided by the overlying glacier. The extreme salinity of the brine lowers its freezing point significantly, allowing it to remain liquid even in sub-zero conditions that would solidify ordinary water. And yet, despite this explanation, the system is still not fully observed in real time. Much of what is known comes from sampling at the glacier's surface and from geophysical inference. The interior dynamics of the subglacial reservoir remain largely hidden. This limitation leaves room for continued investigation. Some researchers have noted that the microbial ecosystems within the brine appear highly specialized, adapted to conditions of extreme isolation, low energy availability, and high salinity. These organisms may represent one of the most extreme examples of life on Earth, existing in conditions analogous to environments hypothesized on icy moons such as Europa or Enceladus. In this sense, Bloodfalls becomes more than a geological curiosity. It becomes a window into the limits of habitability. However, even within established scientific frameworks, certain aspects of the system remain active areas of research. The exact pathways through which brine migrates beneath the glacier, the long-term evolution of the reservoir, and the stability of microbial communities over extended timescales are still being studied in detail. There is also the broader question of how such isolated systems respond to external environmental changes. As Antarctic ice dynamics shift due to long-term climatic trends, even deeply buried subglacial reservoirs may experience changes in pressure, flow, or connectivity. What remains consistent is the visual paradox of Bloodfalls itself. Liquid water, flowing in a place defined by extreme cold, emerging from a glacier as a streak of deep red across a white landscape. It is a reminder that even in the most seemingly static environments, complex chemical and biological systems are active beneath the surface. And so, as the narrative continues, from atmospheric recovery in the ozone layer, to acoustic vibrations in the ice, to hidden rivers and microbial snow, and now to iron-rich brines beneath glaciers, a larger pattern begins to emerge. Antarctica is not a frozen void. It is a dynamic, layered system where chemistry, geology, biology, and physics interact across scales of time and depth that are still being mapped. And as Bloodfalls continues its slow, intermittent flow from beneath Taylor Glacier, one final question lingers in the cold air. If liquid water, chemistry, and microbial life can persist for hundreds of thousands of years beneath solid ice, what other isolated systems might still be hidden beneath Antarctica's surface, quietly active, waiting, and still only partially understood? From the slow, intermittent flow of Bloodfalls, where iron-rich brine emerges from beneath Taylor Glacier like a pulse from a hidden system, the narrative continues deeper into Antarctica's concealed interior. Each discovery so far has hinted at a continent that is not still, but layered, dynamic, and interconnected in ways that only gradually reveal themselves. And now, the focus shifts once again beneath the ice. Far from the McMurdo Dry Valleys, where red-tinted water seeps across frozen rock, the Antarctic interior rises into a different kind of enigma, one not marked by visible movement or chemical staining, but by absence itself, a space where something should be visible, yet is not. Beneath the East Antarctic ice sheet lies a vast region of bedrock that was long assumed to be relatively uniform and stable. But as radar mapping techniques improved, scientists began to detect something unexpected: irregular gravitational signals and subtle distortions in ice flow that suggested large-scale structures hidden beneath the ice. These observations led to the identification of a massive subglacial formation known as the Gamburtsev Subglacial Mountains. Unlike mountain ranges visible on Earth's surface, the Gamburtsev Mountains are completely buried beneath more than a kilometer of ice. They do not appear in any direct visual landscape. Instead, they exist entirely through geophysical inference, mapped through radar echoes, seismic readings, and gravitational modeling. What makes them particularly remarkable is not only their existence, but their preservation. Geological theory suggests that mountain ranges are typically subject to erosion over millions of years, gradually worn down by wind, water, and tectonic processes. Yet the Gamburtsev Mountains appear unusually well preserved, as if they were somehow protected from the full range of erosional forces that shape exposed mountain systems. Mainstream geological explanations propose that the surrounding ice sheet played a key role in this preservation. As Antarctica transitioned into a deep freeze millions of years ago, the growing ice sheet may have effectively sealed the mountains beneath a protective layer, insulating them from surface erosion. Over time, this burial preserved their structure in a near-pristine state. In this interpretation, the Gamburtsev Range is a relic of ancient tectonic activity, frozen in place beneath the ice, offering a rare glimpse into Earth's deep geological past. But even with this explanation, many aspects of the system remain active areas of research. One of the central questions concerns how such a large mountain range could exist beneath the center of a stable continental ice sheet without significantly disrupting its flow. Ice sheets are sensitive to underlying topography. Even subtle variations in bedrock elevation can influence the direction, speed, and behavior of ice movement above. Yet in the case of the Gamburtsev Mountains, the ice above flows in ways that are still being carefully modeled to understand how such a large buried structure interacts with overlying ice dynamics. Radar data suggests that the mountain range is not uniform, but composed of peaks, valleys, and ridges, creating a complex subglacial landscape that influences ice thickness and flow patterns across vast distances. And still, the full structure remains unseen. Everything known about the Gamburtsev Mountains comes from indirect measurement. There has never been a direct visual observation. No human has stood upon them. Their contours exist only in data reconstructions, three-dimensional models built from signals that pass through ice, reflect off buried rock, and return to sensors at the surface. This limitation gives the feature a unique scientific character. It is both real and entirely hidden. Beyond established geology, the existence of such a well-preserved subglacial mountain range also raises broader questions about Antarctic evolution. How did this structure form in the first place? Some models suggest ancient tectonic collisions deep within Earth's crust, possibly comparable in origin to other major mountain systems. Others point to long-term stability in East Antarctica that allowed ancient formations to remain relatively undisturbed over geological time. The age of the Gamburtsev Mountains is still under investigation, with estimates spanning hundreds of millions of years. Their formation may be linked to ancient supercontinent cycles, long before Antarctica assumed its current polar position. What is clear is that their current state is inseparable from the ice above them. The ice sheet does not simply cover the mountains. It interacts with them continuously, shaping flow patterns, influencing stress distribution, and responding to the underlying topography in ways that are still being refined in models. In this sense, the mountains are not separate from the ice system. They are part of it. And so, as the narrative continues, from atmospheric recovery above the continent, to microbial snow on its surface, to subglacial rivers, buried lakes, iron-rich brines, and now hidden mountain ranges, a deeper pattern becomes visible. Antarctica is not a single uniform mass of ice. It is a stratified world, composed of interacting layers: atmosphere, ice, water, rock, and life. Each layer influences the others, often in ways that are only partially observed. And beneath all of it, structures like the Gamburtsev Mountains remain locked in place, silent, unmoving, and entirely hidden from direct view, which leads to a final reflection that lingers beyond measurement or model. If entire mountain ranges can exist beneath kilometers of ice without direct observation, shaping ice flow and preserving ancient geological history in complete isolation, then how many other structures, geological, hydrological, or otherwise, are still waiting beneath Antarctica's surface, still unmapped, still unconfirmed, and still quietly shaping the continent from below? From the buried peaks of the Gamburtsev Mountains, hidden for millions of years beneath kilometers of ice, shaping the slow, unseen flow of Antarctica's interior, the narrative shifts once more toward the surface atmosphere, but this time not upward into distant layers or global systems. Instead, into something far closer to the ground, something that appears almost delicate, yet emerges only under some of the most extreme conditions on Earth. In the stillest regions of the Antarctic plateau, where wind can pause into near silence and temperatures drop far below human tolerance, the air itself can begin to reveal a subtle transformation. Not in storms or clouds, but in the fine structure of the atmosphere immediately above the ice. Here, in conditions of extreme cold and stability, a rare optical and physical phenomenon can occur. It is known as diamond dust. At first glance, it does not resemble weather in any conventional sense. There are no towering clouds, no visible precipitation in the way snow or rain is typically understood. Instead, the air appears filled with a faint shimmer, an almost invisible suspension of microscopic ice crystals drifting slowly downward or hovering in place. Under certain lighting conditions, especially during low-angle sunlight or under artificial illumination at polar research stations, these crystals catch and scatter light in such a way that the air itself appears to sparkle. The effect is subtle but unmistakable, a quiet brilliance suspended within the atmosphere, as though the space between ground and sky has become lightly crystallized. Mainstream atmospheric science explains diamond dust as a product of extreme radiative cooling near the surface. When the Antarctic plateau loses heat rapidly under clear skies, the near-surface air can become so cold that water vapor directly transitions into ice crystals without forming liquid droplets first. This process is known as deposition. The resulting crystals are typically tiny, often hexagonal in structure, and fall extremely slowly due to their minimal mass. In calm conditions, they can remain suspended for extended periods, creating the visual impression of a glittering haze. This phenomenon is most common during winter and in the interior of the continent, where temperatures are consistently low and atmospheric moisture is limited. It is also frequently observed near research stations, such as those located on the high Antarctic plateau, where clear skies and stable air masses allow the crystals to persist. From a physical standpoint, diamond dust is not unusual in itself. It is a natural consequence of extreme cold and atmospheric stability. Similar processes can occur in other polar or high-altitude environments, though rarely with the same clarity and persistence observed in Antarctica. And yet, The phenomenon continues to attract attention, not because it defies physics, but because of how it transforms perception. In environments already defined by visual uniformity, endless ice, minimal contrast, and vast horizontal emptiness, the presence of suspended ice crystals introduces a subtle shift in how space is experienced. Light is no longer simply reflected from a surface. It is scattered through the air itself. The boundary between atmosphere and landscape becomes less distinct. Researchers working in these conditions have described moments where visibility seems both enhanced and diffused at the same time. Objects appear softened at their edges. Distance becomes harder to judge. The air feels denser, not physically, but perceptually. These are not anomalies in a scientific sense, but expected outcomes of light interacting with particulate matter in extremely cold, dry air. Still, the experience of diamond dust can feel unusual to those encountering it for the first time. Beyond its optical properties, diamond dust also plays a role in the local radiation balance of the Antarctic surface. Ice crystals suspended in the air can reflect and scatter incoming solar radiation, influencing how heat is distributed near the ground. Even small changes in crystal concentration can subtly affect surface energy exchange, contributing to the finely balanced thermal environment of the Antarctic interior. In this way, diamond dust becomes more than a visual phenomenon. It becomes part of the continent's energy system, a thin, dynamic layer that mediates the interaction between surface ice and atmospheric processes. Yet even with this understanding, certain aspects of its behavior remain difficult to fully generalize. The formation of diamond dust depends on a precise combination of temperature, humidity, and atmospheric stability. Slight variations in any of these parameters can determine whether crystals form, persist, or dissipate. This sensitivity makes it both predictable in theory and variable in practice. Some observations suggest that under exceptionally calm and cold conditions, diamond dust can persist for extended periods, creating a continuous shimmering layer near the surface. In other cases, it may appear briefly and then vanish as wind or temperature shifts disrupt the delicate balance required for its formation. From a broader atmospheric perspective, this sensitivity reflects the extreme stability of the Antarctic interior. It is one of the driest and coldest environments on Earth, where small changes in energy transfer can have visible effects on the local environment. And yet, even in its most scientifically grounded interpretation, diamond dust carries an almost quiet sense of unreality. In an environment already shaped by uniform whiteness and vast spatial emptiness, the presence of suspended crystalline particles creates a visual texture that is subtle but persistent. It transforms air into something partially visible, turning an invisible medium into a faintly illuminated field. This interplay between light, ice, and atmosphere is not unique to Antarctica, but it reaches a level of clarity here that is rarely observed elsewhere on Earth. Beyond established science, broader reflections sometimes arise, not as alternative explanations, but as considerations of perception itself. How does a human mind interpret an environment where the distinction between air and matter becomes visually blurred? How does spatial awareness adapt when the medium through which sight operates becomes partially structured by microscopic crystals? These questions do not challenge the physical explanation of diamond dust, but rather explore how environmental conditions shape experience. As the narrative continues, from subglacial mountains hidden beneath ice, to iron-rich waters flowing from glaciers, to atmospheric chemistry recovering above the continent, and now to crystalline suspensions drifting through polar air, a pattern becomes increasingly clear. Antarctica is not defined by a single layer or process. It is a stacked system of interactions, where even the air near the surface participates in subtle exchanges of energy, light, and matter. And so the image remains. A frozen continent under a vast, still sky, where the air itself can become faintly luminous with drifting ice crystals, shifting perception just enough to remind observers that even the most stable-seeming environments are quietly active. And as this sequence continues, another question emerges in the stillness between visibility and atmosphere. If even the air above Antarctica can transform into a structured field of ice crystals under the right conditions, how many other subtle atmospheric processes remain unnoticed simply because they exist at the very edge of what human perception can easily distinguish?